This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. Got with me Chuck Nice. Chuck it, baby.
Hey, hey, Neil.
All right.
If you were captain of the Starship Enterprise, where would you go first and why? And of course, we have to suspend disbelief and say that warp is real. So traveling at beyond the speed of light is now a capability. So now that gives you the option to leave this galaxy, go anywhere you want in the observable universe.
I would stick in my own galaxy.
Oh.
Because there's not enough we know about it. So let me just know my backyard first.
Alrighty.
All right. And then I would take a tour around the galaxy, left to the solar system's own motion. That takes about 200 million years for one trip.
Cool.
And so, that's still fast given the scale of all of this. But the sun and all the planets and all the comets and all the asteroids and everybody is all moving around the galaxy together.
Nice.
Okay. Now there's something happened on the internet recently. Of course, if we are going around the sun,
correct, and
the entire system is orbiting the galaxy,
right,
it means we don't complete a closed orbit around the sun. All orbits are corkscrews.
Right, because the galaxy is also moving.
Well, the solar system is moving within the galaxy. Right. So if you followed the path, so there was all this attention given to someone showing the video of this and saying, "Oh, this is a new theory of the solar system. Oh my gosh, did the experts know this?" So it's like, people, this is just two motions simultaneously.
Right.
Okay. If you do this, you orbit.
Right.
If you go that way, it's a straight line.
Right.
If you do this and that, you get a helix.
Right.
Yeah, a corkscrew.
Right.
Right. So
it's like when you drop a ball on a plane.
Well, it goes straight down to you.
Straight down
but if I'm watching you, the ball actually went forward at 500 miles an hour.
Exactly.
Yeah.
It's cool.
But so did you. So I would do that. That's just but then I'd go straight to the center and observe the supermassive black hole dining upon stars that have come too close.
What do you think unlocking the secrets of dark matter could do for us scientifically? Would it lead us to being able to harness it?
We have no idea what dark matter is. I have my own preferences, but my preferences don't matter. What matters is what experiments are active and in progress. And right now, the going thinking is that it is a category of particle that simply doesn't interact with us electromagnetically. So electromagnetism is like light and magnetism and all the things that make atoms stick together as molecules. So you are held together by electromagnetic forces. This would be a category of particles that does not interact with our electromagnetic forces, which means they just pass right on through like you're not even there.
Right.
But
so how do you observe something like that?
Gravitationally. Okay, so we have the only reason why we know there's dark matter here is because, we have some galaxies, but add up all the matter in those galaxies, it doesn't account for what's going on in this part of the neighborhood. Because you see galaxies from behind whose light gets lensed according to Einstein's general relativity. And you can ask, how much mass does it take? How much gravity does it take to lens by that amount? And you come up with a number way bigger than simply counting the galaxies that are there.
Right.
Something else is happening. So we call it dark matter because we don't know what else to call it. It's like I said, I've said many times, it's really dark gravity.
Right.
It's literally dark gravity.
Right.
We don't know if it's matter. The folks betting on it think it is matter, and there's a new kind of particle that we have yet to isolate. That's all. That's what
cool.
that. So if we do isolate it, what would you do with it? Or, you put it in your hand? No, it'll pass right through your hand because it doesn't interact with your hand. All right. So I don't know how you would contain it.
How do you contain it?
You would need a dark matter box.
Right.
So who's going to make the dark matter box? I mean, it's a philosophical problem.
It really is.
If there's a thing that passes right through you,
how do you contain
it? You need something that interacts not only with our forces, but also with its forces.
Exactly.
That could be yet another frontier of discovery in the universe.
What is that intermediary thing?
If you were that civilization, you'd be badass. Oh my gosh. You control not only all the universe that we know about, but the rest of the universe that's influenced by dark matter. You'd be able to grab it, make dark matter planets out of it, if you can make it stick to itself. So, yeah, that would be a powerful posture to purvey.
Can you explain to us in mortal language how the boson gives mass to matter?
Oh.
So how does Higgs work, the Higgs boson? How does it give mass? How does it give mass?
Yeah. So let me attempt this, okay?
That's a lot.
So you need to think of mass not as mass in the traditional sense and not in this explanation. Think of it as inertia. Okay? So inertia in common parlance is the tendency of something to want to stay in motion.
Right.
But it's also the opposite of that, or the inverse of that. It's the tendency of something to not want to move.
Right, to stay at rest.
Okay?
Right.
Okay. So inertia is whatever the thing's doing,
it wants
that's
to do
what
that.
It wants to keep doing
That's
that.
it.
All right? That's it. Okay.
Inertia.
Okay.
Lazy.
So you can measure the mass of something by finding a way to measure the inertia that it wields.
Gotcha.
Okay, so now watch. Let's go to Hollywood.
All right.
And we're going to a Hollywood party. So Chuck Nice walks into a party.
Right.
In Hollywood.
And
the bar is on the opposite side of the floor.
Okay.
Okay? It's a crowded party.
All right.
You want a drink.
Okay.
You walk straight to the bar.
Absolutely.
You'll get there in 10 seconds.
Of course I will.
Okay. Beyonce walks in.
Okay.
She wants to go to the bar. But what happens? She has a very high famous person mass because everyone wants to be around her. And so her posse moves slowly through the room.
Gotcha.
And if you move fast, you have low party inertia. She moves slow. She has high party inertia, a resistance to going fast. Okay? So you have low resistance to going fast. You just walk right across the thing.
Right.
So think of it as the party field. Okay?
Okay.
The party field is giving mass to the particles moving through it.
Gotcha.
Okay? That party field is like
right, because those
is
are
like
the
a
party,
Higgs field.
Those are the party goers. Right.
The Higgs field is like they're like the party goers in Los Angeles.
In Los Angeles.
Okay?
Right.
So you got that? So if the more famous you are, the slower you can move through a crowd because everybody wants a piece of you.
Right.
All right. So in that way, Beyonce has a very high party mass. You have a very low party mass.
Correct.
And to get everybody else in between.
Gotcha.
So that's kind of what the Higgs field is doing. It is the resistance to movement of the particles that pass through it.
Hey, Neil, does time move faster at the expanding edge of the universe and slower at the center?
If you're moving away from me,
right,
in an expanding universe,
right,
and you have a clock that's ticking seconds, okay? If I watch that clock, consecutive seconds that I observe will come to me more and more delayed.
Right.
Okay? So when I observe you, it will look like you have slowed down.
Right.
But as far as you're concerned, you're just running a stopwatch. That's right. That's right. So when she talked about the expanding edge, if you're going to watch that edge, you will see things slow down in that place.
Right.
Okay? But it's not an actual edge.
Right.
It's not a physical edge. It's just it's a horizon where that's all that is. If you go to that edge, now you're in the middle of a new horizon that is itself whatever distance away it would need to be if you did the math on that.
Right.
So the way to answer that is if you want to make any of that true, it's the opposite of what she said.
Gotcha.
You'd be observing objects evolve more slowly on the edge, the expanding edge, and you relative to you.
Right.
Yeah.
Gotcha. Is there any theoretical way to destroy a black hole?
Oh, yeah. You just wait around. Small ones evaporate faster.
Right.
Big ones, like the ones in the centers of galaxies, they might take, I don't know.
A trillion years?
Much longer. Google years. I'll give it a Google. By the way, Google people is an actual number.
Yeah.
And it was a number before it was the name of a corporation. Okay.
Yeah.
And it's spelled differently, Googol.
Right.
Google. 10
Well,
to the
they
100
actually misspelled it.
Yeah, they misspelled it for the company.
Right.
So Google years is a 1 followed by 100 zeros. Then you can evaporate the seriously large, massive black holes in the centers of galaxies. And yeah, then in that future, it'll be a universe with nothing, because all the stars would have died. The proton would have decayed.
Right.
So the very foundations of matter would have broken up into fundamental particles.
Right.
And
really all you have is particles.
Particles.
That's
exactly.
all you have.
That's all you have.
Right.
The fundamental particles of the cosmos. So the universe will end not with a bang, but with a whimper.
Cool.
And not in fire, but in ice.
Which is more likely, extraterrestrial contact celestially or interdimensionally?
Oh, definitely physically. Dimensions, no. Access to higher dimensions? Come on now.
Right.
I think we even did a thing on going to the fourth dimension from the 3 dimensions, 2 dimensions.
With the sphere that drops through a piece of paper.
So if you have an intersection of dimensions, the consequences can be extraordinary.
Yes.
So if we live inside a sheet of paper and a 3-dimensional being says, I've got this sphere, and they don't even know what a sphere is, all they have are circles. Ha, 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 right? So a circle is a sphere in 2 dimensions. Or a sphere is a circle in 3 dimensions. So you can say it either way.
Right.
So if I'm a mighty 3-dimensional creature and I take a sphere, a hollow sphere, and I pass it through your universe.
Right. My paper universe.
How would you describe this? You say, oh, there's a dot. Where did that dot come from?
Right.
It's mysterious.
Right.
Then the dot becomes a circle.
Right.
Now, you only know it's hollow in the inside because I have to open up a portal so you can look in. Otherwise, it's just you wouldn't know it's hollow.
Right.
But anyhow, so it's a circle. And what happens to the circle? It grows. Until what size?
Until it's the diameter of the
Until
sphere.
the full diameter of the sphere.
Right.
And then what happens?
And then it would shrink.
Shrink down and then becomes a point and then disappears completely. And you have to explain that to your friends.
Right. That is so cool.
So imagine a 4-dimensional thing passing through our universe.
Right.
That would be, how would you even describe? You'd see a cube show up in the middle of nowhere and then disappear.
Right.
Right? That would be the 3-dimensional slice of the 4-dimensional hypercube passing through our 3-dimensional world.
Wow.
So in other words, the 2-dimensional slice of the sphere is a circle passing through your paper world.
Right.
The 3-dimensional slice through a 4-dimensional hypercube is just a cube.
Right.
So the cube will start small, get bigger, and then shrink down again, disappear. So I don't know how to access another dimension. I wouldn't even know where to begin. So I will bet that we will contact extraterrestrials before we know how to go in and out of higher dimensions.
Right. But the idea would be that, so here's what I want to tack onto this though. They would know how to observe us, but how would we ever be able to observe them?
If they're a higher dimensions,
yes, they're the higher dimensions.
They could observe us, and we would not even know they were there.
Never even know they were there.
Correct.
So then, okay. And so then, what we would only be able to observe is what they are able to put into our.
No, not to put into it, but to pass through it.
Not put in, but pass through.
Correct.
Our reality.
Yes. I guess they could put it in our reality, but it would be so. Their reality is so much richer. They'd want to just pass it through.
Right.
It's like, so let me give the paper people something to play with, and you just draw a circle. That
Right. Exactly.
Right.
That's not going to do much.
Yeah. Right.
So we would observe that. We would never be able to observe their universe
unless we had access out of our dimensions to their dimension. That's correct.
Wow.
Now here's something interesting. Ready?
Go ahead.
If you're a 2-dimensional being,
right,
and you have skin, so you draw the skin. Well, you have an insides.
Okay.
We 3-dimensional beings would be able to see inside their bodies. The heart, the lungs, the mouth, the eyes, everything.
Right.
But they would not be able to because they can only see in the paper, and they would just see the outer skin, which is just a line.
Right.
What that means is a 4-dimensional person can see every one of our organs at all times. So surgery, the future of surgery could be 4-dimensional surgery, where they come at you from a 4th dimension and never have to cut you open.
Do you think it's possible we'll find complex organisms like fish in the liquid water masses in the planets and moons of, he says, our solar system?
Yeah. Okay, so first, a fish is a way complex organism, all right? Generally, when biologists speak of complex organisms, they're not talking about fish.
Right.
They're talking about multicellular creatures that might have some appendages. They might have, like at the Cambrian explosion of life. When was that? 450, 500 million years ago.
Right.
We went from single-celled creatures rapidly when the conditions changed on Earth to multicellular life. And that multicellular life had like limbs and eyes and it had features that you could talk about and point to.
Right.
Generally, we call that complex life. Okay, and then you want to.
So how about it's a single cell organism, but it has propulsion, like cilia or like,
you mean a way to move around? No, that'd still be simple. If it's single cell,
that's
simple.
Is still not. It's
correct.
Simple. Okay.
Correct.
Even if it's moving or
even it can do all that. But we're talking about I got legs and I got eyeballs and I got a nose and ears, that sort of thing. That's complex
features, as you said.
So the question was, will we find something? Okay, I want to find life in the oceans beneath the frozen surfaces of the moons of Jupiter and Saturn. And I want there to be life there. Mm-hmm. But if there isn't, okay. Right. But if there is life, it'll be something that swims. So our ocean has many things other than fish that are alive. We have coral. Right. We have, what else? You've got sponges. I mean, think about it. It'll be at least as exotic as the range of creatures that are exotic in our own ocean. Right. Exactly.
And the funny thing is, the deeper you go in our ocean, the more exotic the life becomes.
Yeah. Well, the less you've seen it before. Oh, just one thing about the previous segment's question.
Yeah.
Asking about what kind of life we might find if we find life in the oceans and things. It's not only if there's water there.
Right.
Okay. I just want to get thermodynamic on you.
Okay.
Okay.
Go for it.
All right. As far as we know, whatever life is, it will require metabolism.
Okay.
All right. It'll have to process energy in some way.
Okay.
For it to process energy in its environment, there has to be a place that has more energy than in another place. Mm-hmm. So that there's energy flow. Okay.
Yes, exactly. Like our sun.
If the entire ocean were exactly the same temperature and there were no water currents and there was no source of energy, we don't know how life could come to be or exist or even thrive.
So life does not happen without a transference of energy.
Correct. And technically you'd call that an energy gradient.
Okay.
Okay.
Right. Gotcha.
So that's what you need.
All right.
And so under there's sources of energy from like the gravitational stress from Jupiter and from Saturn and other moons on those moons. And that pumps energy like deep in the center. And so
wait, no.
if it's hotter in the center than in the edge, then we're good.
So you mean the gravitational forces of the planet that this moon is orbiting causes the tidal forces causes an undulation that creates energy heat like when you bend a paperclip back and forth.
A better example would be when they say, if you're going to play racquetball, let's warm up the ball. And what are you doing? You hit the ball. You squeeze it and it pops back in. Every time you
deformation and a restoration.
And every time you do that, you're pumping energy into the ball from your racket. That's what's going on to those moons right now.
All right, that's
dope.
That's really
dope. And the hottest moon in the solar system is called Io, and it's closest moon to Jupiter.
Right.
And it's feeling this ferociously, and it's got the most ferocious volcanoes that ever were, because it's hot in the middle. The stuff has got to get out, it's hurling every day.
That is basically from gravity. That's all.
Gravity stress.
Gravity stress.
Yes.
Stress of gravity.
Pumping it. And it's, by the way, it's outside of the Goldilocks zone.
Right.
So we used to think, you need the sun and it's got to be just right. And no, you just need energy.
Right. People. Let's talk about low orbit.
Does it make sense to you that people, this is like inside baseball here, okay? Right. Just be ready for this.
Okay.
Does it make sense to you that on Earth's equator, people weigh a little less than people anywhere else on Earth because of the centrifugal force of Earth's rotation?
Okay.
Okay, the equator is moving the fastest.
Right.
Basically 1,000 miles an hour.
Okay.
Because we have 25,000 miles in the circumference. And how long does it take Earth to rotate once?
24 hours.
About 24 hours. See, divide those.
All right.
It's about 1,000 miles in an hour. About.
All right.
Okay? All right. If you had a different latitude, the circle you take in 24 hours is smaller. Right on down to the pole, where Santa's got no circle at all. He's just pirouetting. Okay?
Very nice.
All right. So, yes, we're rotating as a solid object, but the folks moving the fastest are right on the equator. And I forgot, I did the calculation once. They weigh about, 4 ounces, about a quarter of a pound less.
That's a lot.
Yeah, no, it's a lot. No, it's measurable with a household scale.
Yeah, I was going to say, I thought you were going to come up with some
micro
yeah,
something. No, it's real. It's real.
Whoa.
Okay.
Okay, that's cool.
And,
that's cool. So far, so good.
So let's spin Earth faster.
All right.
They'll weigh even less.
Okay.
Poor Santa, his weight doesn't change at all. So let's rotate it. Now you weigh a pound less. Or kilogram less, whatever's your favorite unit. We just keep doing this. And you can ask yourself, at what speed must I rotate Earth so that you don't weigh anything? You'll just float there on the equator. That's an askable question, isn't it?
It is.
If I'm spinning you up and you're weighing less and less and less,
right?
You know what speed that is?
What?
You rotate the Earth once every 90 minutes.
Every night, instead of 24 hours.
So if I'm on the equator now and my feet aren't even touching the ground.
Just floating.
I'm just floating.
Right.
Yet somehow I'm staying with Earth as you had always been, even up to that moment.
Correct.
Up to that moment, you're there. Now you just weigh 1 pound. You can jump high, but you're still rotating with Earth. You rotate Earth a little extra. Now you're just floating. I just described for you orbit.
Oh.
Low Earth orbit. So low Earth orbit is now, of course, low Earth orbit in practice, you want to be above enough of the atmosphere so you're not, burning up through the atmosphere.
Of course,
right? So you want to be high enough. So that you go up 100 kilometers, about 60 miles. You're high enough above most of the atmosphere so that you can now orbit the Earth faster than the Earth would take you. And you complete one orbit in 90 minutes. If you're right exactly above Earth's surface, it's actually 88 minutes. Okay.
Right.
88. If you do the math, it's 88 minutes.
Yeah.
You go up to where the space station is about 90 minutes.
Gotcha.
Okay. All of that's low Earth orbit. LEO, we call it.
LEO.
Affectionately.
Low Earth orbit.
Yeah. You go a little higher up.
Right.
500 miles up, that kind of thing. You get to MEO. Medium Earth, middle Earth orbit.
Okay.
Not middle Earth.
Right.
But middle Earth orbit. Okay.
Right.
And there you'll find the GPS satellites.
Okay.
All right. So they'll do an orbit. It'll take longer than an hour and a half, but slower than 24 hours.
Okay.
Okay. Then you go a little higher. You get GEO. Geosynchronous orbits. So these are orbits where now, you can do the opposite and say, if I go farther away, I can stay in orbit with a lower and lower speed. Okay? And here's Earth turning beneath my feet. Is there a distance where I can orbit exactly with the rotation of the Earth so that I take one orbit in 24 hours? Yes, there is. It's 23,000 miles up, and it's called geosynchronous orbit.
And there's the synchronicity.
There's the synchronicity.
Wow.
So you launch that satellite, it just hovers overhead.
That's very cool.
And if you park between Europe and the United States, you can beam signals up to it, and you can talk to beyond the curvature of the Earth.
That's it.
Elon Musk wants to launch constellations of satellites so that you don't have to beam out to 23,000 miles. You know why? Because if you beam a light signal 23,000 miles, that's far enough away that the round trip, you notice that in telecommunications. It's a lag.
There's a lag.
It's a lag. You'll notice it. And sometimes you'll see it in a broadcast or even sometimes you've been on a phone and there was a lag. That's probably hitting a geosynchronous. So communication, you want the satellites to be lower.
Right.
But if it's lower, you're not always in view of it.
Right.
Because its orbit's out of your zone. It doesn't stay with you. So now, if once this goes out, you want another one coming in right behind it.
Right.
That's why Elon is launching hundreds of satellites so that everyone has fast internet and with no lag.
If a faraway planet emits a light of low frequency and light of high frequency, which one of them will win the race and reach us first?
The speed of light in a vacuum does not discriminate by frequency. However, if it goes through a medium, it does.
Gotcha.
And it is because different frequencies move through media at different speeds, that the colors manifest after it comes through.
Okay.
So if you put light through a prism and you put it in at the right angle, at the correct angle, the white light comes in and the prism says, blue, you're coming out first. Red, you're coming out last. I'm spread. And since it's spread, since they go through at different speeds, all the colors reveal themselves as they come out of the prism.
There you go, separating in the process.
Yeah. So the prism is glass.
Right.
That will air will separate the colors.
Right.
Diamond does it the best. It's the most transparent. It's the densest transparent thing we know.
Okay.
So that'll do it the most.
Slows down the light
the most.
better than anything.
And it slows down light by to 40% of its vacuum speed.
Yeah, of course that makes sense. Which is when you look at a diamond and it refracts all the light.
Yeah,
and you
the
see
light
all
reflects
the pretty colors.
all the pretty colors.
Right.
That's what's going on.
Oh,
And it does that better than glass does.
Right.
That's why diamonds are diamonds and glass are glass. So different frequencies of light do travel at different speeds through a medium, and just to make that clear. And so now there is medium in space, like gas clouds. When light comes through there, you get this effect.
Right.
You get this effect. And you can get a time lag in an explosion if the explosion happens in multiple frequencies. You'll see it happen in one frequency before it does in another. And we have coordinated our telescopes to check for this.
Nice.
You have a radio telescope, a visible light telescope, a infrared telescope, and you can see phenomenon if it's coming through a medium that will differentially slow down the frequencies of light. No, it's very cool.
That is excellent.
Yeah. But in a vacuum, speed of light is the speed of light is the speed of light. So we have Jennifer Wiseman. Jennifer, welcome.
Thank you.
I think you're your first time visiting
It's
here.
wonderful to be
here. We go way back, but your first time. So
yes.
It's long overdue. And I got your pedigree here. Senior project scientist for the Hubble Space Telescope at the NASA Goddard. What's the full
Space Flight Center?
The Goddard Space Flight Center in Greenbelt, Maryland.
Correct.
Right outside of Washington, D.C. And you're primarily responsible for making sure Hubble is as scientifically productive as possible. And sure enough, that's what it has been. We're going to get into that.
Yeah, there's a lot of good stuff.
And you're professionally, what would you say is your cosmic specialty?
I'm interested in how stars continue to form in interstellar clouds. So
all those pictures from Hubble with the stuff with the clouds,
yes,
that's her.
No, there are people all over the world studying different aspects of how stars and planetary systems around them, presumably, are continuing to form.
So,
cool.
but it's you're in the right place to be fed.
Absolutely. We're just we're blessed to be fed with all this new information from the Hubble Space Telescope and also telescopes, all kinds of other telescopes in space and on the ground. We use them all together in complementary fashion.
So you kind of layer the information to put it together and get a dare I say it, a better picture.
I think of it like a symphony orchestra. The conductor is pulling out some parts of the music from the trumpets and some from the percussion and some from the violins and so forth. But all together, it gives you the full piece of music. So astronomers use some information from the Hubble Space Telescope, some from other space telescopes, some from telescopes on the ground. They all have some different niche. You know, they get some different colors or parts of the wavelength spectrum or a different types of fields of view and precision. And we use all that together to answer the questions we have about galaxies or stars or planets or whatever we're interested in.
So tell me, you don't just happen to be at the Goddard Space Flight Center. That's where Hubble is controlled.
The Hubble Space Telescope control room is, yes, at the NASA Goddard Space Flight Center.
Then what's that Hubble building on the campus of Johns Hopkins?
At Johns Hopkins, we have the Space Telescope Science Institute, which is a wonderful place with hundreds of scientists and other specialists who work with us at Goddard to help us manage the daily science operations of Hubble, to help with the selections of which proposals that are sent in from around the world actually get the time on the Hubble telescope.
I don't think people think much about that.
Yeah.
The data just show up.
What's done is that scientists around the world will write a written proposal for why they want to use the Hubble Space Telescope. Why are the observations they want to do so important to advance science? And why do they need the Hubble Space Telescope to do that?
Okay.
As opposed to any other telescope
Exactly.
that they could be applying for time on.
Right.
Because you don't want to waste. I think this is true for the Allocation Committee, they're not going to give you time for a proposal that you could do on a ground-based telescope.
Okay.
Because space-based telescopes are so expensive and so precious every moment of observing time. Right?
Exactly.
Yeah.
So you have to make the case. Why is it important that we use this precious time with the Hubble telescope to observe this particular galaxy or this particular exoplanetary system? And why do we need the Hubble telescope or the particular instruments that are on Hubble to do that? And that goes through a pretty stringent peer review process. We have specialists come in and review all the proposals and rank them. And in the end, basically 1 in 4 or 1 in 5 get time on the Hubble Space Telescope. Although I should add that we're pretty good about storing this data. So once the observations are done with Hubble, the data are put in an archive that's easily accessible. And so scientists around the world often go into that archive, pull out data that's already there, but they can use it for something else. And in fact, about half of the results, the peer-reviewed, published science discoveries and results coming from Hubble now are based on data that scientists have taken out of that archive.
So if you use the telescope, then everything that you glean from using it is now open source.
Well, it's better than that, I think.
Is it better?
No, because I had my own motives for observing that part of the sky.
Right.
Yeah.
But maybe you have another thing you could extract from the data that I haven't thought of yet.
Right.
That's right. Exactly. That's right. So it's
but there is nothing proprietary.
Well, there is some of the proposals. The proposing team gets a few months of time to do what they actually propose to do and do it well, because we want them to have the time to do it well.
Okay.
And then the data gets put in this archive, and then it's open to everyone. And there are other types of observations that are generally done, like big surveys and things that let's say the director of the Space Telescope Science Institute decides would be a good general purpose use of Hubble, and that data immediately goes into public purview. So it can be immediately used by scientists around the world, but anybody in the public can reach the archive. We also have an image gallery that I think is probably of more interest to most general people in the science interested public, and that you can find at our websites, nasa.gov/Hubble or hubblesite.org. But these have the images, the things that you really think about when you think of Hubble's galaxies or
your
nebulae.
Desktop screensaver.
Your screensaver,
Yeah,
exactly.
That's where you go, and that's just all free to anyone around the world to use and enjoy. And that's something I'm very proud of about the Hubble mission, is that we've made all of this data and all of these images free for anyone around the world to use.
That's why Shutterstock hates you.
I got one more inquiry here. I don't think the public knows that there's some allocation of time that, I mean, you hinted at it, but I want to hear more. So is it still true that the director can just say, here's a good idea, everyone will benefit, let's just do this, it's not going through the telescope allocation committee? Okay, so it's a director's discretionary time. Does that still exist?
It does. So the director of the Space Telescope Science Institute, who currently is Dr. Kenneth Sembach, has a certain allocation of time with Hubble each year that they can use for what they think is the most some scientific purpose that might not come through sort of the general competitive process with scientists around the world. And usually this time is used for, let's say, a kind of big survey or a general purpose observation that will be of use to people for many years to come.
Could it be used for something that's a little quirky?
Well, let me assure you that we take great care in choosing the directors of the Space Telescope Science Institute. We've had excellent ones.
I'm going to refrain.
And so I'll mention a couple of these that I think are particularly noteworthy.
They're not political appointees, I think is the point.
Yeah,
okay,
right.
The current Space Telescope Science Institute director, Dr. Ken Sembach, has very wisely allocated director's discretionary time to do a lot of observations in the ultraviolet part of the spectrum, looking at stars and star-forming regions that radiate light in this high energy frequency range. Well, why is that? Well, that's because Hubble is really the only general purpose telescope right now that can see in the ultraviolet. And you have to be above the Earth's atmosphere to see in the ultraviolet because of the filtering effects of the atmosphere. This is important to get this data and get it in the archive while we can, and then we can use it for many years to come. There's another director's discretionary project that I think is really noteworthy, and this came from years ago. A previous director, Dr. Bob Williams, used his director's discretionary time to just point off in a direction of space where there weren't very many nearby stars to drown out the image and just collected light. Some people did push back on this and said this is a very valuable time on this telescope. It's a lot of competition. Why would you, quote unquote, waste your director's discretionary time this way? But basically it was, let's look and see. We think there are probably some faint galaxies that will pick up by just integrating light, receiving light for days, but we weren't sure. After several days of doing this, the result was this image that's now iconic. It contains thousands of little smudges of light. They are all galaxies. It's called the Hubble Deep Field, and we've done some subsequent ones called like the Ultra Deep Field.
It's one of the most famous images
it certainly
from Hubble.
is.
Yeah.
And it's my favorite. Yeah. But it really showed us visually what we may have suspected already just from the physics and the cosmological theories, but that our universe is filled with galaxies, and they come in many different shapes and sizes. And of course, the intriguing thing about getting these feels is that you're seeing all these galaxies in one picture, but of course, the ones that are actually farther away, you're seeing them as they were farther back in time.
Right.
So if you can somehow tease out which of those galaxies are closer to us and which of them in that image are farther away, and compare their differences. Are they different in their morphology? Are they different in composition? Sometimes you need other telescopes to get that information. Right. So it's a true time machine that you can now see visually, and Hubble really set the foundation for this kind of pictorial study of galaxy evolution. And I think it's just a wonderful accomplishment. But that was based on a very wise but brave use of director's discretionary time with the Hubble Space Telescope.
With naysayers all along.
Yeah.
And also, once the Hubble sort of pitches tent right there, other telescopes can say, I can now get different kind of information from that same place. Let me go to the same place.
Exactly.
Wow.
So it's probably one of the most observed spots on the sky today.
Certainly is. So we now have we have other positions on the sky also that have been observed in these kind of deep field ways using different kinds of telescopes, like the Chandra X-ray Observatory, or
one of Neil's favorites.
Telescopes on the ground. And all of these telescopes have different capabilities, and so they complement Hubble and are giving us a tremendous understanding of how the universe has changed over time.
Yeah, there you
go. That's really cool.
Yeah.
All right.
What are 2 or 3 discoveries that laypersons like myself can reference when talking to others about the fantastic contributions Hubble has given us? Right now, all I can say is it took some really pretty pictures of some stuff, and I need better ammo for those of us not literate in astrophysics.
There are some profound discoveries in different realms of astrophysics that Hubble has really made a groundbreaking, if you will, or space-breaking, if you will, a contribution. One of the first things Hubble did was to confirm that there are, in fact, supermassive black holes in the cores of galaxies. It was theorized that was the case, perhaps, but one of the first observations Hubble did was to look at the core of another galaxy. M87, for example, is one of these other galaxies that we knew was kind of active. We could see that there was like a high-speed jet coming out of the core, but we weren't sure what was causing these types of things. Hubble looked at another external galaxy and saw that the gas moving around the core of that galaxy was moving very fast. And so when you have something orbiting very fast, but you don't know what it's orbiting, you can pretty easily calculate what the mass of that material is based on the distance from the core that the material is moving and its velocity. And the only thing that could be that massive in such a small volume had to be a supermassive black hole. Wow. So Hubble then became what we call our supermassive black hole finder, because with subsequent instruments on Hubble, we actually looked at the cores of lots of other galaxies and confirmed over and over again that supermassive black holes are often, if not always, perhaps in the cores of galaxies.
So what went implied but not stated there is you needed Hubble to do that because Hubble has very high resolution.
Exactly, right.
Other telescopes, it's just a smudge, and you can't find something so close to a tiny center.
Exactly.
Right.
Yeah, that's a point that needs to be made. The reason Hubble is there at all is because we put it above the atmosphere. The atmosphere has a blurring effect on light coming through, and it even filters out some types of light. So Hubble being above the atmosphere gives us very high resolution observation.
Nice.
Exactly. And that's why we were able to use Hubble to discern this gas right around the cores of other galaxies. And on one side, it seemed to be moving away from us very fast. That would be the red shifted gas, and on the other side of the center of those galaxies, we'd see stuff that appeared to be moving toward us very fast, blue shifted light. And so you can tell that the material is orbiting very fast, and from that calculate that the only thing that would create orbits that fast would be a lot of mass condensed in a very small volume, and the only thing that answers that question are supermassive black holes.
So now let me ask you, as you talk about this process, what immediately comes to my mind is the process. How long does something like this take, or is it that you are doing mathematical interpolation or making extrapolations from a period of time that you're looking at the information?
Well, I have to say it all depends. So an observation, depending on what you're doing, like I mentioned, that deep field took several days of observations. Others, if it's something bright, if it's just one pointing, you can do it maybe in an hour or two.
Oh.
But then you need to go through some processing time for the data comes down, but it needs some data processing. In that case, usually we can get images out if they're just simple snapshots within a few days.
Wow.
But if you're doing scientific analysis, like you're doing a proposal to answer some question that requires quite a lot of analysis, maybe comparisons with data from other telescopes, these kinds of things, that can take months or a year, sometimes even years. So it just depends on the complexity of the question that's being asked and that's being in the data, how the data are being used.
Right, and then you submit the paper, gets peer reviewed.
Okay.
Yes.
Then maybe they want adjustments to it because you didn't dot your I or cross your T. Then you do that, satisfy the reviewer. Then it gets accepted for publication. Then it gets scheduled. Right. And so that adds a chunk of time at the end there as well. But
so now that makes me think of another question. I know we're short on time, but what happens if somebody is looking for something, or they say, propose this, and then the peer review comes back and says, no, but then you find something even bigger? Has that ever happened?
These observations typically go through 2 peer reviews. One is to get the time to use Hubble in the first place. So that means that they generally had a pretty good idea of why these observations would be useful. Right. And then there's the second one, when after they've done the analysis of the data and they submit their analysis to the professional journal of what they think they found. And true enough, the journals can actually say, we don't actually think this is right or profound, and maybe choose not to publish it. But usually they do. What's interesting, what's interesting is that data that may have been used for the initial proposer's purposes is now available for other researchers to use. And as we discussed about the archive, they can pull that data and find something that the original proposer didn't even think of to use with this data. And that has happened quite a lot. Let me tell you why.
It becomes a whole other research paper.
It becomes, and the reason is because Hubble has been around so long, 30 years now, of often taking sometimes repeated observations of the same areas in the sky for different purposes. We can now look back and see things that have changed over time, which is very interesting, in particular in our solar system, looking back at images of, let's say, Jupiter over time, year after year after year, and then starting to compare these images and saying, whoa, as we look back at this data that maybe have been taken for different purposes in earlier years, but we can see trends. Let's say that big great red spot on Jupiter, it's a big storm, but as we look over the decades of
Chuck, you know what its official term is?
No.
Jupiter's red spot.
We're trying to make it clear. The great red spot is there, but it is red.
It is a spot.
However, It is shrinking as we look at these images year after year after year. Like, whoa, this storm is changing. It's changing in color. It's getting smaller. We see new storms cropping up. So this is one of the benefits of having a telescope operating so long and being able to look back in that archive at data that may have been taken for some other purpose, but then stringing it all together, and we see how things have changed, are changing over time.
What is the most interesting, unexplained thing we have observed with Hubble? Is there something that astrophysicists are still trying to work out?
Love it.
A couple of things come to mind. Hubble is observing a lot of effects of what we call dark matter. And so we can't really see dark matter, and we don't know what it is. It's a mystery, but Hubble can see where it is because it's distributed pretty heavily in these clusters of galaxies. We can see the galaxies, but we know there's a lot more stuff in there because Hubble sees what's called lensing of light coming from behind those clusters of galaxies that's traveling through that cluster, and it gets distorted, it gets magnified and stretched out. And so background galaxies look kind of strange when they come through these regions. And we can, because of that, we can map out where the dark matter is, but it's still a mystery as to what it actually is. And even more mysterious is something we call dark energy, because this is a surprise. We were looking we've been, for all of Hubble's mission, we've been measuring very carefully the expansion rate of the universe. That was one of the original goals of Hubble. But just a few years ago...
Wasn't that one of the original reasons why it was named Hubble?
Well, exactly.
Because Edwin Hubble himself discovered the expanding universe.
Exactly.
And so that if this telescope was going to go all in on that, you might as well name it after the guy who put it on the map.
Exactly.
Yeah.
So Hubble was... One of the first goals of Hubble was to measure better the rate of the expansion of the universe. We expected that as we became better able to look at more distant galaxies, which is looking back at time and measuring the expansion rate at that time and comparing it to the expansion rate in the current epoch, that we would see that the expansion rate of the universe has been slowing down. That was the expectation because gravity basically is trying to pull things together and perhaps slow down this expansion. The surprise in recent years was that by comparing Hubble observations with also observations from good telescopes on the ground, and looking at the difference between the expansion rate in the distant universe, meaning far in the past, with the expansion rate in our current epoch, that the universe expansion rate has actually in recent epochs, meaning in recent billions of years, been getting faster. It's accelerating. It was first decelerating, and now it's accelerating. We don't know what's causing that. Hubble's a big player in this discovery. It's not the only player, but it's a big player. And so now this is a whole new enterprise in astrophysics, is trying to understand what is it that could be accelerating the expansion of the universe.
Does Hubble have any sufficient technology to keep up with the needs of today's understanding of the universe? And will there ever be a telescope with a 360 panoramic view like Google Street Maps?
This is a very good question. And we need both, because we want to be able to see everything in the sky. And we have survey telescopes that are designed to do just that, to have big fields of view and to survey the entire sky, often for a particular reason. So right now, for example, we have the TESS satellite that's surveying the sky, but looking specifically for stars that may have planetary systems around them in our nearby neighborhood.
Is it fair to think of TESS as a follow-on to Kepler?
I think so, yeah.
And TESS, get me through that.
The Transiting Exoplanet Survey Satellite, I think. I'm going to have to remind myself. But anyway, the idea of TESS is to do just that, survey. There's a telescope being designed for the ground, the Large Synoptic Survey Telescope. The whole idea of this is to do the whole sky survey very frequently. So it's a good idea. However, when you're doing that, you're not getting the precision in small fields of view that you can get with a telescope like Hubble. So it depends on the purposes at large. If you really want a high angular resolution, precision, high sensitivity observation of something, That's a different goal than doing a whole sky survey. And we sort of need both of that. So the best way this works is if you're doing whole sky surveys, and then if you find something that you'd really like more detail about, then you hone in with some other telescope to do that. Hubble is really not good for these whole sky surveys. It's much better for pointing and getting much higher angular resolution. My favorite example of this is the Orion Nebula. I love the Orion region of the sky. It's a very famous constellation. I did my own doctoral research on star formation in this region of the sky.
Isn't the closest star forming region to us?
It's the closest region of massive star formation, so stars bigger than our sun.
All right.
But they light up these massive stars. Once they form, they're so powerful, they ionize the surrounding gas, so you get these beautiful nebulae. So the Orion Nebula is famous. Hubble can peer into that Orion
Jennifer was
Nebula.
born in the Orion Nebula.
Anyway, I love the Hubble image of the Orion Nebula because it does give you that great detail. You can see massive stars, you can see the colors, but you don't get the big field of view that you can get with other telescopes.
What are the projects that you think will be the most important for this current decade?
Hubble is poised to be a major player in these astrophysics discoveries in the coming decade. So one of them I've already mentioned is kind of getting a better grip on this idea that the universe is expanding at an accelerating rate. How's that? Why is that? And how is that working?
Yeah, who ordered that?
Exactly. And so telescopes like Hubble will be working in concert with other observatories. The Wide Field Infrared Space Telescope, or WFIRST, is a telescope idea that's being developed and right now that will be a large, again, one of these big fields of view that can kind of give us a better sense of how galaxies are distributed and how they've become distributed over time, and that's related to dark matter and dark energy.
Just remind me, wasn't WFIRST a retooled, decommissioned military telescope?
Right. We took a telescope that had another purpose, and now we're re-envisioning it to do this kind of big surveys of in the infrared,
which helped reduce the cost ultimately.
That was the idea. Although sometimes
that sounds like a no.
Retooling things has its own complications. But it is going to be a terrific telescope. I think
when I say military, I meant spy telescope.
The name of the game, I think, for the coming decade is complementary cooperative work. Let me tell you, one of my favorites is that Hubble is being used in complement with probes that we're sending out to other planets in our solar system. And we get much more information this way than we would by just Hubble alone or just the probe alone. For example, the Juno probe that's at Jupiter right now is getting all kinds of information about Jupiter's magnetic field and gravitational field. And Hubble is back here orbiting the Earth, looking at Jupiter, and Hubble has the unique ability to see the ultraviolet light coming from the auroras, the magnetic poles of Jupiter, and those are dancing around relevant to what's happening with the magnetic fields around Jupiter that Juno is measuring in situ there. So this cooperative work gives us a lot better understanding of these magnetic fields and what's happening on Jupiter and even its moons than we could.
So it's not an after the fact conjoining of data.
No.
It's an in situ.
Yes,
that
exactly.
is beautiful. I love that.
Cool,
right.
yeah.
We're doing things cooperatively with Hubble. Another example in just the recent past was when the New Horizons probe went past Pluto. As New Horizons was on its way out there, Hubble was used to find other undiscovered moons around Pluto and to help New Horizons, help us chart a good course for New Horizons, and even to help New Horizons to know what objects to look at beyond Pluto. So these are things that I think are examples of how Hubble and other telescopes are going to be used cooperatively in the coming years to give us a lot more information than we could from any observatory alone.
Wasn't there also a mission? I have a memory where there was a probe to an asteroid where it dropped a projectile, which would then kick up asteroid dust
And then collect?
in a direction and an azimuth and an angle so that was it Hubble that would then be able to see through the dust and get a spectrum
Well,
of it?
that was the idea. Yeah. So it kicked up dust. It was observed by quite a few
Oh,
telescopes.
it's quite a few telescopes.
And
okay.
I would have to, to look into the details of what was found. But I thought that was a really nifty idea.
So it's another exple of
Right,
I'll do this and
the
then you do that.
collaboration,
Yeah,
yes.
yeah. Cosmic collaboration.
Yeah. By the way, what a brilliant idea.
Yeah,
To
yeah.
drop a projectile and kick up the dust and then look through it.
Look through it with
That's-
ground-based telescopes or space-based telescopes.
Yeah.
A huge topic of interest for the coming decade, which is the whole topic of exoplanets.
Oh.
And this is where telescopes will be working very cooperatively. We didn't even know back when I was in graduate school if there were planets orbiting other stars other than our sun. Now, because of telescopes on the ground and telescopes like Kepler in space, we know of thousands of star systems that have planets. And so now we can presume that most stars have at least one planet. Hubble will be being used in the coming decade to do more analysis of the atmospheres of these exoplanets, complementing work from telescopes like TESS, that's looking around for nearby systems that have planets, and
So that finds the
future.
system, then there's the handoff to Hubble to analyze the system.
Yes, and other telescopes too. Also, the James Webb Space Telescope that will be launched in 2021 will be looking at exoplanetary systems in the infrared part of the spectrum, and that will complement Hubble's observations of these exoplanetary systems. Hubble can see a little in the infrared, but mostly in visible and ultraviolet light. And so we'll be getting this wonderful suite of information by using Hubble in complement with other telescopes about the nature of exoplanets.
What is the plan for Hubble as its final photo, and when will that be? What's the lifespan of Hubble? How long?
Yeah.
How long can this go on?
Well, that's a great question. You know, Hubble was launched back in 1990 from the space shuttle, and it was designed to be continually replenished with the space shuttle missions, which we did for a lot longer than we originally expected. So we're not servicing it anymore because the space shuttle program is over. We're now building a new future spacecraft. We've got what we've got with Hubble, but Hubble's working very well. The last astronaut servicing mission we did back in 2009 was very successful, and they've left the telescope. The astronauts went up and put in some new science instruments and repaired some other instruments and some other equipment on the telescope. It's a satellite orbiting the Earth, and Hubble is doing very well right now. I will tell you that one of the astronauts, John Grunsfeld, who is an astronomer himself, brought with him
And a friend of StarTalk. He's been on several times. Yeah.
He brought with him a model of Galileo's telescope. And so up there on the space shuttle during the last servicing mission, we had this marvelous juxtaposition of this model of Galileo's telescope from 400 years ago.
The first telescope. Yeah.
And out the window of the cockpit of the shuttle, you could see the Hubble Space Telescope. And so it was just a wonderful visual of how the progress of engineering and curiosity and optics all work together. So Hubble is working very well. And so we don't really have an end date of Hubble in mind. The kind of stated NASA position now is as long as Hubble is being scientifically productive, we'll keep operating it. And it looks like, just from looking at the health of the gyroscopes and the batteries and the science instruments, that we'll be able to get good science from Hubble for probably through the end of this decade and maybe even beyond.
Not bad.
And that's great because we want it to be operating while other telescopes are also operating with complementary capabilities.
Right.
The James Webb Space Telescope should launch in 2021, and it will be a fabulous space telescope tuned into infrared wavelengths of light.
Right.
And so in the infrared, you can peer at galaxies that are very distant in space and time. Their light is getting redshifted as it travels through expanding space to get to us. And Hubble can't see that far into the infrared spectrum of light. So Hubble can see very distant galaxies, but the Webb will see galaxies even a little bit farther back in space and time.
We're going to
And,
emphasize
yeah,
something you just said because it's remarkable to me.
Yeah.
All right. So we are seeing infrared light from galaxies in the early universe who in the early universe were emitting visible light.
Right.
Okay.
Or even ultraviolet.
Or even ultraviolet.
Right.
And that
Since
all got
cooled down.
redshifted
Exactly.
Right.
over to the infrared part that the James Webb Telescope is tuned to see.
That's
Nice.
Right. So we're folding in that
Exactly.
knowledge of the universe
Right.
to nab those galaxies right when they're being born.
Right.
I like to put it this way. The universe we think at least the universe that we know and love, started about 13.8 billion years ago.
Okay.
And Hubble is seeing all the way back right now to baby galaxies from within that first 0.8 of the 13.8 billion year history of the universe. And the Webb will see even closer to the beginning of the universe within a few 100 million years of the beginning of the universe. You can see basically
the cradle of creation.
Infant galaxies, because what these telescopes are seeing are the first, after the first gas formed from the first atoms, which formed from the first subatomic particles, you finally get enough gas to form stars. And these stars and gas coalitions, if you will, are what we call the first proto-galaxies. Right. And that's as far back. That's what the Webb telescope will be seeing. And over time, these little baby galaxies began to merge together and form bigger galaxies. Right. And these grew over cosmic time into the galaxies we know and love today, like our own Milky Way, which is the product of several mergers over time.
Right. Yeah. And has there been any recent collisions that we have seen of galaxies?
Well, of course, it takes a long time for galaxies to actually merge. But Hubble, actually, that's one of the wonderful discoveries of the Hubble Space Telescope is that merging is common and was more common in the early universe. So with Hubble, we've looked out into distant space, looking back in time, and we've seen quite a few cases where galaxies are either in the process of merging or they've already merged. And that merging process creates distortions in the shapes of these galaxies because of the tidal pulls and the gravitational pulls. And it's quite interesting. We believe that our own Milky Way is set to merge with our nearest neighbor, big spiral, grand spiral, the Andromeda. Yeah. And we're on a head-on collision course. That's something Hubble helped us find.
Would it be possible if NASA ends funding for Hubble or it comes to its regular end, someone like Elon Musk could buy the rights to the scope and send his own repair missions, thereby now owning the telescope?
The current plan is we'll operate Hubble for as many years as it is scientifically productive, and then when it's not no longer providing good science, it will cease to function. Eventually, we'll need to either push the satellite itself either to a higher orbit, we call it a parking orbit, or else help direct it safely into the ocean.
Pacific Ocean.
Yeah, well, I don't know exactly where. But as for private company involvement, we don't have any official plans for that right now. But let me tell you, there's a lot of energetic discussions out there. So, stay tuned for coming years.
I love that idea. Right. If it's Hubble's, we're going to plunk Hubble in the Pacific, or someone can buy it, I think.
Let somebody buy it, right? And continue to receive information.
Let me add this, though. Astronomers think about this very hard all the time. What's the best kind of facility to have to do the kinds of astrophysics we want to do? And there comes a point, such as came the point with my own car recently, where you have to decide, is it worth it to put a lot of money into continuing to refurbish something that's decades old, or is it better to build something fresh using newer technology? So, Hubble's not in that situation. We hope Hubble will be operating for much of the next decade and beyond. But at some point, the decision will need to be made as to whether the kinds of capabilities that Hubble does could be better done with a new telescope. And in fact, there's some wonderful concepts being developed right now for Hubble follow-ons.
Okay. Fantastic. All right. What is your favorite Hubble discovery?
I'll slip into my favorite Hubble discovery. It doesn't sound flashy, but is actually looking at things like the ultra deep field and finding out that galaxies themselves change in amazing ways over billions of years. And Hubble being the time machine that it is, we can actually map out by looking at distant galaxies and comparing them to nearby ones how they've changed.
So this ultra deep field is even deeper than the original concept deep field.
That's right. And then one image that I just love, it's nothing special, if you will, but it's just a beautiful galaxy. It doesn't have a beautiful name. NGC 1309, I just think is a gorgeous spiral. So those of you listening to this, go out and Google NGC 1309 Hubble, and you'll see a beautiful spiral with some interesting galaxies in the background. NGC 3603, NGC 3603 is a beautiful...
So if someone Googles that, they'll go to this image online.
Yeah, if you use Hubble in the name, you'll see this cluster of newly formed stars surrounded by beautiful ionized gas, a kind of purplish nebula. And to me, this just shows great beauty in the universe. and how our telescopes are enabling us to see these kinds of beautiful active regions that we haven't been able to see in such detail before in human history. And this inspires all kinds of things, even beyond science, art, science, philosophy. All kinds of things are inspired by the observations we can do with Hubble and other telescopes today, and I'm grateful for that.
So, Jennifer, you have any just concluding reflective thoughts beyond what you have, the reflective thoughts you've already shared?
I think that the Hubble Space Telescope has shown how we can use, as humanity, we can use technology to do something that not only enhances our scientific understanding of nature but also gives us a sense of unity. There are people all over the world from every nation that are excited about the Hubble Space Telescope and what we're seeing. And it gives us, I hope, a sense of unity as citizens of Earth, that we're part of a magnificent universe, an inspiring universe, something to look up at and be inspired by, and to keep our sights, our spirits high. I think astronomy inspires all kinds of
positive
thoughts of beauty and philosophy and theology and art and music, and all of these things are part of what it means to be human. So keep looking up, I'd say.
Today, we're going to be talking about the human condition. That is centerline to what StarTalk Special Edition is all about. And of course, if it's special edition, it means we've got Gary O'Reilly.
Hey, Neil.
So, Gary, tell me about the human condition and what's going to happen today.
All right. I suppose in many ways this is the specialist edition, because we are talking about the science behind the things that make us different, that make us special. And that's, as a species, makes us adaptable.
So what makes us special, which makes our species special?
Yeah.
Among all species of life on Earth.
Okay. I mean, humans have survived and thrived in just about every location, every climate on Earth. Well, so far, that is. Things are changing. This adaptability has seen the human form take many different body shapes, sizes, blood types, and skin colors. Yet, with all this uniqueness, we are 99.9% similar in our DNA. So
999.
Yes.
Yes, it's
right?
even more than 99.9, but go ahead.
Okay. Now seems like a good time to understand a little more about the diversity and our diversity and adaptability through the lens of evolution and biology. So if you would introduce our guest.
Professor Herman Pontzer, welcome back to StarTalk, dude.
Thanks for having me back.
So right now you're a professor of evolutionary anthropology and global health at the Duke University's Global Health Institute. And you're a recognized researcher in human energetics. I love it. Human energetics and, of course, evolution, which is fundamental to that. Author of a 2022 book, Burn, and in 2025, Adaptable, How Your Unique Body Really Works and Why Biology Unites Us. Can we think of our adaptability as some kind of superpower distinguishing us from all other animals on Earth? Because I've thought long and hard, what is special but we can't fly, we don't run fast. Almost everything that would kill us in the wild is because the other creature is better at it than we are. So to think of our adaptability as a unique feature of being human, I got to hear more from you on that.
And we're the shifters, the change, the shape shifters, right? We can be successful anywhere on the planet because we've got this crazy kind of dual inheritance that we talk about. We have all these cultural things that we inherit from generation to generation about how to survive in different environments. We've got this body that's we might be generalists in a lot of ways, right? We're good at a lot of different things. Maybe we're not as good at sprinting as some animals, as good at climbing, but we can kind of do it all fairly well. And we end up getting everywhere across the entire planet. Think of another species. I don't know if you could.
No.
That's been as successful in as many climates.
Wait, Herman, the bacteria in your gut are traveling with you.
Well, I wanted to call the book Protein Robot because I like to think of us as like these kind of damp RVs trundling along the Earth, right? With all of our microbiome on board, like passengers with us.
In the subtitle of your book, Why Our Biology Unites Us. So what are we to make of that subtitle?
Yeah, well, so I don't know of any other species that has the sort of adaptability range that we do, right? Everything from the ways that we learn how to make a living growing up because we have these different cultures that help us adapt to different environments, to our physical characteristics that are a little bit different across the globe in different ways, often as a sort of local adaptation to different contexts. Skin color is a great example of that. Body proportions are another example of that. And so we are, all of us, expressions of this sort of shared common superpower that our species has, right?
Oh.
That adaptability is actually the expression of this, the diversity is the expression of the adaptability. And so, I think rather than thinking about it as dividing us, it actually is showing our common origins in a way. When I was writing this book, it was 2022, 2023. And I thought, well, maybe this whole discussion about, maybe the sort of universe-wide discussion about diversity and all those debates are going to be passé by the time the book's out. And so I'm glad I'm glad it came out when it did. I think, the goal is to have it be this sort of common ground. I want people to understand how the bodies work, why we're all different, how diversity happens, and have it be a kind of common ground that we can talk about these kind of big, often polarizing ideas and discussions with a common, a common set of facts, common evidence base.
You have your work cut out ahead of you because everything you're saying that unites us, our culture uses to divide us. So you got some work cut out to you to change the definition of diversity in that way. Yeah. Just letting you know.
So, Herman, is there such a thing as a textbook average human? And what are the dangers if we start to perpetuate such a thought process?
Yeah. So, no, there's not, right?
Arithmetically, there has to be an average. So your question should have asked, is there a normal person?
Well, what's normal?
Right, exactly. That's a different thing. There's always an average. You can always take an average, but it's
here's what I would say about that, Neil.
Yeah.
To push back a little, is my introduction to human diversity began in undergraduate in my coursework, but my actual physical hands-on introduction to this was dissecting a human, right?
Ew,
and
you did that?
Yeah, we were in medical school. I didn't go to medical school, but I took the medical school gross anatomy class at Harvard. And so it was me and 50 aspiring doctors, disassembling a person on these big dissection tables. And every day you show up and you get your tools out of a little case and you start taking a person apart. And, 3 months and 160 pounds of human later, you've seen everything. But what you learn very quickly, and the reason, you might think, like, why do we bother doing that? It's kind of an old-fashioned way to do science or to learn medicine. But the reason you do it is that you immediately learn that, the branching of arteries through your torso as it comes out from your aorta and starts to feed all your organs, that pattern of branching is not the same for everybody. And in fact, often you find a branching pattern in the person that you're dissecting that doesn't match any of the variants shown in your dissecting text, right? And that the nerves are the same way. And, and that's just the stuff you can see with your naked eyes, right? That our diversity is down to the core. And so I would say, if you think about like a parts list for humans, right? I'd be curious to think about this, but maybe it's 30,000 different parts that all kind of come together to make you up. I would bet that just in the same way that there's never been a perfect March Madness bracket, there is no human that all the pieces match a textbook dissector piece for piece. Because you might be right, you might be similar to the dissector on 99% of them, but there's 1% where you differ, and there'll be a different 1% that I differ, et cetera, et cetera.
So the mathematical way to say what you just did is whatever average you might obtain, it's not useful because the variance is so high on that average.
Yeah.
Because think about it. I mean, right? You can say an average and you look for someone who matches the average and no one does because everyone is scattered around to the left and right of the average on the chart. So, okay. Yeah. I'm with you on that.
How should that inform us on a sociological level?
Yeah. So, once you start to appreciate how diversity, what it looks like, that it's sort of multidimensional, is not just, for example, skin color in this country is historically used to divide us right into different categories. And if you're black or you're white, you're thought about you're in this category or that category. If you really understand human diversity, you realize that there are sort of subtle differences across all these different modalities, in terms of the way our cardiovascular systems work, digestive systems, skin, of course, sure, nervous systems, all of it. There aren't sort of neat categories that we can box people into. And I think it forces us to see diversity the way that it is, which is, again, the sort of individualized expression of these common forces, right? So it's an expression of our humanness, right? Rather than, oh, you're in this box and I'm in this box, and we can kind of caricature it and pretend that we know something about you just because we put you in this particular box. That's not actually how the body works or how diversity works.
So to that point, I read a pretty cool paper out of, I forget which part of Harvard, but was the basis for the predicate, there's no such thing as race. And that race is a completely manufactured construct. And it was based on what you just said, which is there's no box in which you can put enough people to say, this is what white is, or this is what black is. But the thing that I didn't really understand was how the scientists from Korea had more in common with one of the scientists from the Netherlands than one of the other scientists from the Netherlands on a biological level. Like that was
in the paper too?
That was part of it, yeah.
Oh, okay.
Yeah.
So, I mean, it depends on what they're measuring, if they're measuring genetic differences or that kind of thing. But take this, here's a kind of toy example, but it's a real biological phenomenon. Blood types, okay? ABO blood type, right? So I don't know if you're type A or type B or type O, whatever it is. All of us in the four of us sitting here might have all the same blood type, right? Maybe we're all type A. And that would mean that we have the same genetic variant. And in that way, in that particular locus, that gene, we're all more similar to each other than other people who have type B blood. All right. So in that measure, we're all a group and we're all different from somebody else. If we go by skin color, the amount of melanin in our skin, right? Well, there's differences in that, right? Who has more melanin, who doesn't have as much melanin. And that might break us down differently.
So there's an unlimited number of boxes that you could...
Exactly. And not only that, but there aren't even hard edges on the boxes, because if you look at something like skin color, in this country, we often put people into sort of black or white, but of course, skin color is everything in between too, right? So especially if you look globally, there's no, you get everything pretty dark because you have a lot of melanin in your skin, to very light because you have very little, and there's everything in between. So there's no hard edge where you say, okay, now I stopped this category and I'm into that category.
And of course, President Obama could have legitimately been declared as a white president because he's exactly half white. But by his European mother, right?
Yeah.
But instead, we call them a black president
because of the social norms
he's
in America.
Exactly half black,
right?
Yes. So in one of my books, I forgot which, he imagined him running for president in an African country
as the white guy.
I mean, historically, it's even crazier. Like there were people who, groups who now we consider as sort of obviously white in the U.S. People from Ireland, people from Italy, who in the late 1800s would have been considered black.
Yeah. Yes.
They weren't white until the powers that be, that are, because it's a socially constructed power move to make these groups, until the powers that be decided that they were in the white group, that they became white.
If we look at the latitudes here on Earth, how have humans adapted in terms of their biology to survive at these different latitudes?
Yeah, so that brings up an important point to start with, which is that a lot of the variation that we see in head shape, size, all the different physical characteristics we see, this is all the rage in the late 1800s was how long versus how wide your
phrenology.
head was.
Oh, yeah.
If you were dolichocephalic or brachiocephalic or all these things.
Yeah, I remember that.
So almost all of those kind of variations are just noise and slosh and genetic mutation that's tolerated because there's no strong selection to get rid of it, right? So a lot of the variation that we see, the superficial variation, a lot of that is just sort of tolerated noise. Now, that said, there are cases where you have a strong enough selection pressure that's localized and strong enough and long-lasting for generations and generations that you get local adaptation to a particular circumstance, a particular pressure. So latitude's a great one. So
I have to clarify something here. Correct me if I'm wrong, Herman. When you say adaptation, you mean those who don't have the variation die, so they don't propagate their genes. So no organism adapts, you're talking about the ensemble
Species.
statistics of a generation where only some that happen to have the variation walk through the proscenium into this next world where they can survive better.
Yeah, I just add to that you can, one way to sort of lose that game is to die. The other way to lose that game is to not have any kids.
Right.
Or not have as many
you
as
don't
your
send
neighbor.
your DNA into the future.
Right.
Yeah.
Gotcha.
Gotcha. Okay, pick it up. Sorry.
So latitude is a great example of a pressure that's stable over time. The Earth has been spinning on the same, the equator's been the equator for a long, long time. And it's been hot at the equator for a long, long time and colder towards the poles. And so that heat differential, for example, has shaped body shape, size, and proportions. We see populations near the equator that are, on average, tend to be taller, thinner. Populations near the poles tend to be a bit stockier and heavier. And that's because you want to get rid of heat if you're in a hot environment at the equator all the time. You want to hold on to your heat if you are towards the poles.
So the physics of that, I think we have an explainer on it, where if you are rounder, you are better insulated against losing heat, because how are you going to lose heat? Through your skin.
Through your skin.
Basically.
Yeah. So the more round you are.
Yeah, and if you ever see a pigeon in the winter,
they puff up.
And they're very round.
Or cats.
That too.
Cats do the same thing.
Yeah.
They make themselves round when they're cold.
And we do that too. We'll bring our arms in.
But the fur and the feathers come up and they trap a layer of air.
That helps too. Yeah. But they also try to round themselves. Whereas in the summer, the cat is all esplajado on the pavement.
Yes, that's so true. And it's so funny when you look at lions, they lay stretched.
Yeah.
But when your cat is cold, and they're very similar, they wrap up.
Yeah.
So, okay.
So I just want to make sure that the listener got the physics of what you just implied
Absolutely.
there.
Yeah. So there's a fun field story there, a piece of my research that kind of touched on this in a way I wasn't expecting. We do research in northern Kenya. There's a population there. They're called the Dasnich. They live with their goats and camels and cattle. It's a pastoralist group. They're like the Maasai. You might have heard of the Maasai. It's a similar kind of population. And we started work there in 2017, and we were talking to one of the NGOs, the charities that had set up shop in this little village called Illoret. There's this German charity. We're talking to the head of the charity, and because we wanted to get a sort of health and nutrition research project started, we thought we should talk to people who have been doing health and nutrition sort of outreach. And he said, "Oh, it's terrible. It's terrible here. Everybody, all the kids, 70% of the kids are malnourished here." And we thought, oh my gosh, that is terrible. And so we kind of thought about that and kept that in our minds. And as we're kind of visiting that village and the surrounding villages, it doesn't square, though, with what we're seeing, because these kids don't look malnourished. These kids are running around, happy, laughing, families are big, people look healthy. And so we thought, if they say that they're malnourished, then that's important to know, but that seems, counterintuitive based on just interacting with this population. Fast forward a couple of years, we've got ourselves a big data set on thousands of children who've been measured from the day they're born, every few months, to the time they're 5 or 6 years old. And what you can see when you look at these kids' heights and weights is that they're born around the same size as all the other kids in the world. And then their weight starts to fall off a little bit, but their height grows fast, right? So by the time they're 3-4 years old, kids in this population are taller than 3 or 4 year olds in most of the rest of the world, because they have been adapted. That population has been adapted to be tall and thin. And so this German charity was looking at the ratio of weight, which was the same as everywhere else, maybe a little bit low, to height, which was tall because they were adapted to be tall. That ratio looked bad. It made them look malnourished, too thin, too light.
They're just
for their
skinny.
Height. They're just skinny, but they are built to be skinny.
So once again, there's a European bias brought into Africa to pass judgment on who's there.
It even goes further, because the folks from Nairobi who I was working with, those folks from Nairobi aren't part of that ethnic group. They don't share that same, to the same extent, that same kind of tall, thin body build.
Right.
And so I'm actually more similar to my Nairobi colleagues, even though our skin colors are different on that dimension, than either of us are to this northern Kenyan population that's tall and thin, right? So like the whole, to even begin by using the kind of American racial categorization to try to make sense of what's going on there, you're sunk from
folly.
the beginning.
It's folly.
Yeah. Yeah.
Isn't there an example of adaptability with people in the Andes and then across in the Himalayas? They're living at a similar altitude, but one of them will suffer altitude sickness, one of them won't. Why?
Yeah.
What's up with that?
Yeah.
Yeah. So humans have gone into the high altitude parts of the world. 3 big examples of this. The Ethiopian plateau, and those populations aren't well studied, so we don't know a whole lot about that physiology. The Himalaya, right, Tibet, Nepal, and that's been well studied. We know a lot about that. And the Andes in South America. And these are all independent evolutionary forays into high altitude. And the problem is you don't have any oxygen up there. The air is still 21% oxygen, but the air pressure is so low that there just aren't as many molecules of oxygen available for you to get into your bloodstream. And so everybody's oxygen starved at these high altitudes. And so there have been independent evolutionary changes, adaptations to this same, this real challenge of getting enough oxygen. In the Himalayas, there is an allele that helps determine how much red blood cells you make. So, okay, let me back up. Red blood cells are the cell that carries oxygen. You need that. And they have a tough job at altitude because there isn't enough oxygen to go around. And so what most people do, and most populations do at altitude, you make a lot more red blood cells. Your body responds to the oxygen debt by making more red blood cells. And that's good for a while, but it makes your blood thicker and can lead to altitude sickness. And we still see a lot of altitude sickness in the Andes, for example. They haven't their bodies haven't figured out how to deal with that. In the Himalaya, they don't have this issue of altitude sickness. Why not? Because of this allele that has been gone to fixation. It's completely the norm genetic variant in the Himalaya that helps them deal with oxygen debt without overproducing red blood cells. They produce enough to keep the oxygen going, but not overproduce it and get sick. They also have bigger lungs. They have a bigger spleen, which is this reserve red blood cell tank that we all carry around. So there's a whole bunch of adaptations that go to try to get enough oxygen in.
So where do the Neanderthals fit into that particular scenario in the Himalayas?
Yeah, I wondered if you wanted to go there. So the first thing you have to understand is that humans historically have slept with anything that they encounter. Homo sapiens, we evolved in Africa about 300,000 years ago. And as we sort of become so successful, so adaptable, our superpower at full display, we get into Europe, we interact with Neanderthals there. What do? We admix with them, to use the sterile scientific term, and we have children. And we can still see the genetic evidence of that today.
But a quick question I have to slip in there. You said 300,000 years ago, we come out of Africa, get into Europe, and admix with the Neanderthal implies Neanderthals either left Africa earlier or evolved as Neanderthal in Europe.
Yes.
Now, we know from DNA testing that pure Africans have 0 Neanderthal DNA. So there must have been some deep European origins of the Neanderthal. Is that correct?
Yeah, that's right. Whether it's deeply in Europe or sort of into the Near East is much debated. But yeah, it's outside of Africa. So, humans and Neanderthals, of course, have a common ancestor about 600,000 years ago. Those two branches go their separate ways. Ours in Africa, theirs in the Near East and Europe. And at some point, they become what we would consider to be the Neanderthal gene pool. And when our branch comes back in and intersects them again, we have these matings and this admixture.
And so we are fertile with each other because we have the same common ancestor, even though we're many, many
such
years
a recent one
down from the line. And an interesting fact that I discovered in my own work for Starry Messenger, that book, was we grew up with the archetype of this stupid backward Neanderthal that never stopped dragging its knuckles.
Right.
Then we find out that Black Africans have no Neanderthal blood, yet there's admixtures in current European white people. And
not
only
just Europeans,
then
by the way.
did research papers start saying how creative and inventive. There's a complete shift in the early 1990s. Herman, am I right here?
That's one retelling. I think that's fair to the history of what happened there. I think there was already a reimagining of what Neanderthals were like before that. Populations outside of Africa all have a little bit of Neanderthal in them because as we kind of get out of Africa into the Near East and those matings happen, those genes kind of get washed to every population that's kind of downstream of that, right? So Asians, Native Americans will all have a little bit of Neanderthal in them left over from that kind of crossing event that happened in the Near East and Europe.
Well, that makes sense because it's, those were the crossroads. All those areas outside of Africa were actually the crossroads for human travel. So it kind of makes sense. Yeah.
So there's this great example of another kind of discovery from ancient genome. But by the way, all of this is mind-blowing stuff. It is from DNA that we've gotten out of fossils. And we discovered a whole new species of human ancestor, or human relative, I should say, that's Neanderthal-like in Asia called the Denisovans.
Were they contemporary with the Neanderthal?
Yeah, that's right. That's right. Kind of Denisovans go one way, humans and Neanderthals the other way, and then Neanderthals and humans split a little bit later. So they're even a kind of more distant relative of us in a way.
What's the etymology of Neanderthal and the etymology of
Denisovans. So Neanderthals are so named because those initial fossil was found in the Neander Valley, and in German, valley is Tal. So it's Neanderthal.
Oh.
And that's why it's Neanderthal and not Neanderthal, because Thal is tall in German. Right. That's if you want to get pedantic. And then Denisovans are found that the original site is Denisova. It's a Denisova cave in Siberia somewhere, I believe.
Okay.
Yeah. And they had just a couple finger bones. And those aren't really diagnostic. You can't figure out what species it is just from the bone, from the morphology, the shape of the bones. But they drilled into it, got the DNA out, and go, this is a whole other group. This isn't Neanderthals and it's not Homo sapiens. It's something else.
Right.
And that was the discovery that there is this, unappreciated species that we didn't even know about.
So they got the DNA from the bone marrow?
Any of your bone material will have cells in it. So yeah, that's not just the marrow, but any of it.
Why does DNA last that long? It's a pretty delicate molecule, isn't it?
It doesn't last kind of fully intact. So your DNA, if you stretch it, if you took all the DNA in your body and you stretched it out, you'd be dead. That's the first thing you should know. But second of all, it would get to like the moon and back or something like that, all your DNA stretched out. Then we've discovered that not only is there this other species of human relative, but there's evidence of mating with them as well.
Oh.
So it wasn't just Neanderthals. Damn. It was also Denisovans. And then you find out that this gene variant that has been so key to the success of Himalayan groups, where did it come from? It came from Denisovans.
Wow.
So so there were these mating events with Denisovans. That gene variant ends up in the human gene pool, sloshed around. Doesn't give you any advantage at sea level, Only when those populations begin to go up at high altitude does it turn out, oh, by the way, that variant's actually really good at high altitude. And then it becomes the variant that everybody has because of the selective process of reproduction and survival.
If you were to take pictures of our DNA and superimpose them, what would that look like and how alike or different would we be?
Between us and the recent ancestors.
So Denisovans, Neanderthal, Homo sapien, and then you take those pictures, you kind of superimpose them. What would it look like?
Yeah, so this is exactly what we do when we get the genetics to begin with to try to make sense of it. The best way to picture it is like a tree, right? So imagine a tree where all the branches are very hard and clustered very tightly around the crown. That is the entirety of the human species over here. And then there's a branch that comes off real low and ends up over here somewhere. That's the Neanderthal branch. And then it's like you discovered, oh my gosh, I didn't look closely enough. There's a branch that's even lower and goes out even a bit further. And that's the Denisovan branch.
Okay.
Right? And so if you were to overlay the A's, T's, C's, and G's of the genome on top of each other, you'd find they're very, very similar. All of those individuals, you have to really compare them at thousands and thousands of base pairs to sort of see that clustering, just because all mammals are pretty similar. Primates are real similar,
right?
And so all these human ancestors and relatives are real similar too.
Take me back to when we went from grunts to articulate speech.
Oh, that's an amazing.
What's up with that?
Oh, yeah. So the anatomy of that's pretty well known. The anatomy of the vocal tract, for example, has changed, which allows us to have this sort of two-compartment vocal tract, right? So your larynx is down here real low, and that gives you a vertical component to sort of shape the frequencies that come out of your your lungs as you make noise. And then you have this horizontal component from the mouth, and those get shaped differently and give you all the A, E, I, O, U sounds. So we know the anatomy of speech very well. When that evolved,
Yes.
right, that is really hard to know for sure. And in fact, I don't think anybody knows.
I heard that our ability to form sounds, as you articulately described, the two-dimensionality, the frequency and volume and texture of our vocalizations, that this was a genetic defect, if you will, from whatever was going on in the grunting community. There was some genetic alteration that changed it.
All adaptations start off as mutations. Natural selection is the survival of the fittest, but mutation is the arrival of the fittest. You need variation. You need mutations for natural selection to go, oh, yep, that's the one that's going to work here, and that one's not, right? If there's no variation, if there's no mutation, there's no way for natural selection to happen.
Let's look at this situation of adaptation of our environment. Yeah.
Go.
So our adaptation is being forced to speed up because of the environments we're being pushed into, out of rural farming into town city and cities in particular.
At a rapid rate, that is.
Yeah, as a rapid rate. But are we now being mismatched? Are we being confronted with circumstances that, you know what, this body is evolved for this environment, not that environment? So, for instance, in disease, we have diseases now which are chronic and major, but how long ago were they not, Herman?
Oh, so the populations I live with, hunter-gatherer groups and even farming groups that I work with today, they are heart disease free, diabetes free. So the things that we're going to die from, they're protected against. And of course, the flip side is the things that we're protected against because of antibiotics and vaccines, that kind of stuff, really gets them. But, these lifestyle diseases were only an issue in the last couple hundred years.
Herman, if they're an isolated community, that means there are no outside
influences,
viruses, bacteria, other ailments that could influence them until they meet someone from the outside.
But that question raises the point that I think people get wrong all the time, which is people think that any human population is ever isolated. That's never the case, right? I mean, there are always interactions. There's always gene flow and people flow and migration and movement. So there are no isolated groups anymore. Even these groups that we work with who are hunting and gathering or farming, it isn't that they don't interact with people who aren't. It's just that they like to keep their old ways. They live in a world that they interact with people all the time, but they prefer to keep their own culture. So you raise this issue about accelerated adaptation.
Yeah,
it's the brain, man, because our brains are born unfinished, right? We learn. We've created this entire cultural inheritance that we each inherit and learn. It takes you 15, 20 years to learn it all, so you could be a proper adult, a functioning adult. And so we have all this, and that cultural evolution can happen much faster than our biological evolution can. So we have these two parallel tracks happening all the time. It's a really fun thing about humans.
There was a study done in comparison on back in the day when there were bus drivers and conductors on board, and the health of the driver as opposed to the conductor. Even though they go to the same place, they travel together all the time.
They breathe the same air.
They breathe the same air. They see the same people. One is sedentary. The other is obviously mobile, stamping tickets and checking up and down on the levels of the bus. These are situations now that we have not really been evolved to have a sedentary lifestyle. You talk about the hunter-gatherers in Africa. So what are the overall health implications for modern health now that we're finding ourselves mismatched with?
Yeah, that was a seminal study in the 1950s showing that the drivers who sat all day ended up getting heart attacks at a kind of scary rate.
Yeah.
Their buddies who were walking up and down the aisles had healthy hearts. And so that was one of the early clues that physical activity, daily physical activity, is absolutely essential for keeping your heart healthy. Well, why is that? Well, because we've evolved for hundreds of thousands of years in an active lifestyle. That's the way our bodies are built. So, that's sort of the lifestyle our bodies expect.
So you've got paleo diets. There's no way we're going back to a Paleolithic lifestyle.
No.
So what's our answer here?
Well, the London bus study is a great example, right? Because you have the benefits of activity without having to cosplay as a Neanderthal or something like that. It's an example of how you can have physical activity in your daily life. You guys are New Yorkers. You guys walk around the city and get lots of physical activity.
We meet our step minimum every day.
Yeah.
Right.
Yeah.
And it's not just the steps. The last study that came out about New Yorkers who tend to be thinner than most other places in the country, it's the pace at which New Yorkers walk as well. New Yorkers tend to walk much faster than any other place. Okay. So the two together, the fact that they walk everywhere and they walk briskly is what makes
We're in a hurry even when we don't need to be.
Yeah. Exactly. There's this lovely study from the 70s by this husband and wife team. They looked at the average walking pace of people down sidewalks and how big the city was. They went all over the world to do this. And the bigger, more dense your city is, the faster you walk.
Oh, cool. Okay. That makes sense.
So, Herman, the history of anthropology as applied properly or improperly on our species or on our populations, in almost every case led to some legislation, some laws related to those conclusions, be it to justify slavery, be it to limit immigration. So is there a policy implication that your work would bring to the front that is either progressive or regressive in the history of this exercise?
I think it does have big societal sort of implications, right? When we think about how the body works and we have a fluency in how our different systems work, we use that fluency with how our bodies work to understand diversity. I think that absolutely it's going to. And what it's going to do is it's going to inform how we move ahead from, the really old school ways of thinking about the body were very genetic determinist, right? We move into the 1900s and even recent times, and it's very environmental. It's all nurture, into the nurture-nature debate. And I think we're moving to a third period here where we're in a personalized era, right? Ooh. Whether it's personalized genetics or it's personalized ways of thinking about my health, right? And if we
personalized diet, even perhaps.
Personalized diet. And if we leave that discussion just purely to the influencers or purely to, the political class that doesn't have any fluency in how the body works, or these sort of old school ideas about these sort of caricatures about our diversity, we're going to be in real trouble. So I think that the book does kind of help inform those big discussions we're having right now. Look, whether it's IQ, whether it's sex and gender, whether it's health and vaccines, whether it's, all of these issues that are right, in front of us today, they all fundamentally rest on how we understand how our bodies work and how our bodies work differently. And so, the book isn't trying to get anybody to, I'm not trying to make anybody think like I think, but what I do want to have is people, a common evidence base for us to have those discussions, a fluency that we can have these discussions usefully and meaningfully. So I think there are societal implications. I think the way that they shake out are going to be, hopefully, make things better for everybody.
Thank you for returning to StarTalk.
Yes.
Oh my gosh, we miss you.
It was a fun conversation, guys. Thanks.
Yeah. We miss you. You have a unique combination of expertise that deeply informs what we care about here on StarTalk Special Edition. So that means we want to sort of have access to you further going forward.
Hey, I'm always happy to be your evolutionary anthropologist on call. I'm here.
Delight to speak to you. Thanks for enlightening us yet again.
Thank you.
All right. You know what this topic is today? There's probably no more important topic we've ever addressed than this topic.
Oh.
The future of humanity. And we are featuring my interview with the one and the only Elon Musk. And sometimes he's referred to as the real-life Iron Man, Tony Stark. I have to agree with that, actually. And he's the founder of PayPal. It's an internet company. He's a founder of SpaceX, a rocket company. He's founder of Tesla Motors, an electric car company. And he's chairman of Solar City, a solar energy company.
He is the real Tony Stark.
There you go. And I thought, I mean, I don't love you, but I thought I should bring in some help on this one.
Okay.
Bill Nye.
Yes. Over here biting my lip.
Yeah, good to have you here because you've got some serious engineering background. And so a lot of the show, we're going to talk about engineering the future of our civilization.
Yeah.
And I could make stuff up, but I'd rather you say what real stuff. And plus you're writing a book on what sustainability?
Climate change and doing more with less.
Do you know what it's going to be called?
Unbounded.
Unbounded.
So it's an extraordinary time. I mean, we're talking about Elon Musk and his vision for the future of humanity.
Let's get to the bottom of what created Elon Musk. I wanted to find out, you know, where did he come from? Where did he grow up? I didn't know anything about the man. Let's find out. Elon, what egg hatched you into this world? Where were you before you?
Well, I was born in South Africa.
Born in South Africa, and you come to America and make $1 billion.
Yeah, I mean, I didn't expect to make $1 billion, I suppose. I mean, I grew up in South Africa, honestly, seeing a lot of the same TV and movies and reading comic books, and it really didn't feel all that different from, say, Southern California, honestly.
So you had a kind of baptism into American pop culture at the time.
Yeah. I mean, I ate a lot of hamburgers and went to steakhouses and read like every comic book, you know. So my father brought me on a trip to the United States when I think I was about 10. I remember it was a really awesome experience because the hotels all had arcades. So my number one thing was when we went to a new hotel or motel or whatever it is, go to the arcades. And so
forget any other services. Forget whether they had bed bugs. You're looking for arcade games.
Yeah.
What did video games do for you?
I mean, they're incredibly engaging, and they made me want to learn how to program computers. Because then I thought, well, I could make my own games, and then I could also... I wanted to see how the games work. Like, how did you create a video game? That's what led me to learn how to program computers.
So you became a programmer?
Yeah, so I had one of the first video game consoles. It didn't even have cartridges. It had like 4 games that you could play, and you could like pick one of the 4 games you could play. That was it. And then it went from there to the original Atari, and then the television. And then I was in a store and saw a Commodore VIC-20. And I was like, holy crow, you can actually have a computer and make your own games. I thought this was just one of the most incredible things possible. Took all of my saved allowance and then hounded my father until we got the Commodore VIC-20. And it came with this manual on how to program in BASIC, which I sort of spent all night, several days in a row, just absorbing that. And
on your own? No one forced you?
No, I would never.
This was self-motivated. I got to know this. This is good for me.
I must have been like 9 or 10 or something.
So you were fluent in BASIC at age 9 or 10?
Yeah. I kind of got OCD on the thing. Maybe it's not technically OCD, but I certainly got obsessive. Let me put that, at least the O part.
So programming is power.
Else.
You get to control something.
Yeah, you can construct a little universe. And when you first do it, you're like, wow, this is incredible. You can actually make things happen. Like you type these commands and then something happens on the screen. That's pretty amazing.
So there is hope for all the parents who have middle school children who are lost in their video game.
Absolutely.
They too can be a billionaire. So just a quick resume of Elon Musk. So, in 1999, he founded the company that would become PayPal. Wow. And then sold it to eBay. And he ran off with $180 million in it, and he was 32 years old. And so...
How did he make a living between university and 32?
I don't know. He was like making companies and selling them, and then
the way you do.
On. Yeah. Of course, that's how you do it.
Exactly.
Let's find out.
That's hard.
So what I wanted to know was, while he was in college, what was he thinking about? You know, most of us in college, you want to major, get a job when you come out. Let's find out what he was thinking about.
When I was in college, I sort of thought, well, what are the things that are most going to affect the future of humanity? And electric cars, solar power, essentially sustainable.
Most people are thinking, I just want a job when I get out. And you're trying to reshape humanity as an undergraduate.
I mean, in America, it's pretty easy to keep yourself alive. So, I mean, my threshold for existing was pretty low. I mean, I figured I could be in some dingy apartment with my computer and be okay and not starve. In fact, when I first came to North America, I was in Canada when I was 17. And just to sort of see what it takes to live, I'd try to live on $1 a day, which I was able to do.
Wow.
You sort of just buy food in bulk at the supermarket.
Rice and beans and...
Yeah, I went more for the hot dogs.
Hot dogs, okay.
Hot dogs and oranges. But you do get really tired of hot dogs and oranges after a while. And we can also pasta and a green pepper and a big thing of sauce, and that can go pretty far too. So I was like, okay, if I can live for $1 a day, then at least from a food cost standpoint, well, it's pretty easy to earn like $30 in a month, So,
yeah, I would think.
So it'll probably be okay.
Okay,
Yeah.
so that allowed you to not have to worry about money because you did the experiment.
Yeah, I did the experiment, exactly.
So this was an important psychological, philosophical anchor for you. Not to put words in your mouth, but that's a starting point to launch anywhere you want to go.
Yeah, absolutely.
And so now you've got a baseline, a life baseline from which to go new places, intellectually, psychologically, financially. So what came first? Thoughts of an electric car or thoughts of space?
You know, when you're starting out in college, like in your freshman, sophomore year, like you have these sort of sophomoric philosophical wanderings. And I try to think of, okay, what are the things that seem to me would most affect the future of humanity? There were really 5 things, 3 of which I thought would be interesting to be involved in. The 3 that I thought were definitely positive would be the internet, sustainable energy, both production and consumption, and space exploration, more specifically, the extension of life beyond Earth on a permanent basis. And then although I never thought I would actually be involved in that. That was simply something I thought that was important in the abstract, but not something I thought I would ever have an opportunity to be involved in. And then the 4th one was artificial intelligence, and the 5th one was rewriting human genetics. These were just the 5 things that I thought would most affect the future of humanity.
Bill, you engineer man, do you agree with this list?
Yeah, it's a pretty cool list.
That's a cool list.
I would have included educating women and girls, raising the standard of living of women and girls so that the human population of the world will slowly become more manageable.
A greater tapping the lost intellectual capital.
That's right.
Among those who have been disenfranchised from it. So Elon, after he sold PayPal, what he wanted to do, he wanted to go into space. Let's find out how that got started.
When I started out, my goal was to do a philanthropic mission with the intent of increasing NASA's budget. That was my goal. I was confused as to why we'd not yet sent a person to Mars. It seemed like this was obviously the goal after the moon, and we'd not made progress on that. And when it became clear that PayPal was going to get sold, a friend of mine asked me what I'm going to do next, and I said, well, I don't know what I'm going to do next, but I'm always curious about what's going on with space and why have we made progress. I just wonder when we're going to send a person to Mars. So I went on the NASA website, and I couldn't find a date. I was like, well, maybe it's here somewhere, and I just can't find it. Yeah, there's got to be some schedule or something.
We're looking for that.
Game plan, or it's this date, even if it's far in the future, and it was not to be found anywhere. And anyways, I sort of started learning about that back history, and I thought, well, okay, maybe there's something that I can do to send a small mission to the surface of Mars that would get the public excited, and as a result of that public excitement, NASA's budget would be increased, and we could resume the process of sending people to Mars. Essentially,
so you thought you can do that with your lousy $1 billion?
No, I didn't have $1 billion at that time.
Okay.
I had about 180 million, still a lot. And I figured, well, maybe I could spend half of that on a mission to Mars. So I spent a fair bit of time investigating the space industry and eventually decided on this idea of sending a small greenhouse to the surface of Mars. And we called it the Mars Oasis mission. And so you'd have seeds in dehydrated gel that would land, you hydrate the gel upon landing, and you'd have this great shot of green plants on a red background, and the public responds to precedents and superlatives. So this would be the first life on another planet, the furthest that life's ever traveled, as far as we know. And
that's how you get a headline.
Yeah, exactly. It's got to be something new or something superlative. Mm-hmm. And I thought, well, okay, and that would maybe reinvigorate excitement, and the result would be NASA's budget gets increased. So the whole goal in the beginning was just, how do we get more money for NASA? But after spending a fair bit of time on this, I came to the conclusion that I was actually incorrect. My initial assumption was wrong, because I thought that where there's a will, there's a way, and that we just sort of lost our will. That's false. There's plenty of will. People needed to believe that there was a way, and a way that would not bankrupt the country or mean that they'd have to sacrifice something of critical importance like healthcare. So it became clear that the space transport problem had to be solved. Unless there was a dramatic improvement in the cost of space transport, then none of it would matter.
So in your first successful launch, what was the cost per pound to orbit?
About $6,000.
$6,000. Okay, that's an improvement.
Yeah, not bad.
Not $100 a pound.
No. To get to $100 a pound, you need a big rocket that's fully reusable.
Are you there yet?
No. So far, we've not recovered a stage. But I think we'll recover a stage within the next year and be able to refly.
Is there a date on your website where someone can say, he's going to land on
Touché. Good point.
That sounds like a no.
Well, I've said it publicly many times, although maybe we should put something on the website, which is that I think we've got a decent shot of being able to send a person to Mars in about 11 or 12 years.
So, Bill, what is he going to do this?
To reuse a stage?
Yeah, and then and get the cost down. And,
the cost down to...
Wait, who's going to get us to Mars? Elon Musk or NASA?
So let us keep in mind,
please,
that NASA pays SpaceX.
Okay.
About $2 billion so far.
Okay.
So SpaceX is now a contractor for NASA.
Okay, so our tax money is going to
that's a good thing.
To SpaceX. Okay. Yeah. So what is this vehicle that's going to get us to Mars?
So there's a couple of innovations, just let's say 3 innovations that I've seen with my own eyes, which must hide another 100,000 innovations that are much more subtle. First thing is all the same engines. First stage, second stage, how many stages? It's the same engine.
Okay.
So why didn't somebody else do that? That's a good question.
Everything was a one-off in the past.
Yeah. Well, or a 5-off.
Okay.
Saturn 5-off.
Uh-huh.
And so then the other thing is, let's see if we can reuse a stage.
Right.
And this is his thing. It almost worked the other day. He tried to the company tried to land on a barge just east of Cape Canaveral, and it landed on the barge just a little faster than anybody wanted because it ran out of fuel to slow itself down.
Okay.
But
You
that
need
looks
fuel
like,
to get faster, and if you're going fast, you generally need fuel to slow down.
yeah.
Unless you're going to aero brake or something.
Yeah, well, coming through the atmosphere after lunch, it's and the thing is not shaped for aero braking, really, but it is shaped for retro rocketing, if I
Okay.
can coin the verb.
There you go.
But then the fundamental thing, you guys, when NASA was created, I believe, Dr. Tyson, on the year of your birth, just within a week or so, yeah,
Same week.
they put NASA centers all over the U.S. So when they went to manufacture rockets, they put pieces of the rocket all over the U.S. The solid things are made over here. The liquid things are made over here. They're tested over there. They get on train cars and go down there. Just right there, just the expression, Houston, we have a problem. Why isn't it Florida, we have a problem. Cape Canaveral, we have a problem.
Chuck, did
Orlando,
you know
we have a
that
problem.
the instant the spacecraft clears the gantry, in that instant, full control transfers to Houston.
I mean,
If there's a human being on board.
1,000
Right.
nautical miles away.
Right. All the whole countdown and everything, or go to launch, all of that is Cape Canaveral.
But it's
And then
SpaceX.
the moment it takes,
The moment it passes the thing,
then it's like, all right, guys, we'll take it from here.
SpaceX, it's just south of Los Angeles International Airport. Train car drives up, full of stainless steel, full of titanium, full of let's make rocket-anium parts. And it comes off the train car, they shape it and do their own thing.
I
Weld
want
their own-
rocketanium. I want some of that.
Yeah, well, you can get it. 6061 T6 aluminum, T7 sometimes tempered 7 aluminum. So then it comes down. They make the tank. They attach the plumbing. It comes over here. There's a bunch of electronics. They attach that. They vacuum test it over here. Blah blah blah. Then it goes back on the train car to either Cape Canaveral, close to the equator as the U.S. can get, or up to Vandenberg Air Force Base, which is north of
As a
there.
continental U.S.,
In the
because Hawaii is
continental.
closer.
Yeah, Hawaii's closer, but that's not on a train car.
Yeah, it's not on a train car.
Extraordinary train car. I mean.
Yeah.
Huge reduction in cost.
Is that low enough to go to Mars like everybody says? He wants to go to Mars. He still wants to go to Mars.
Well, I would like to go to Mars, but I want to come back. And I don't want to go to Mars to live. I think that is not all the way thought through, in my opinion.
So, Bill, if we're going to go to Mars, do you see engineering challenges to that, or is it just,
no, piece of
or is it
cake.
only? No, wait. No, I'm going to. This is a very serious question. Yeah. So, my question is it just a matter of money, or even if I gave you as much money as you want, you might not be able to solve some of the engineering problems?
No, we can solve the problem.
Snap.
We can solve.
That's what I figured.
Yeah, because we land a rover from a freaking rocket crane.
Right.
We can solve the problems.
Right.
But as far as this colony idea, everybody.
Okay.
There's no liquid water as such. It's not like there's a river there.
Right.
Okay. Then
If there is, it's underground and no one has found it yet.
Okay, and let me go on to say, it's on its summer day at the equator. It's 20 below. Okay, yeah, you can get, what is it everybody wearing this year? Canada Arctic Crew. That was a Goose Down, Canada
Okay.
Goose Down brand jacket. All very good. That's when things are really good. That's all you got
That's
on.
that's midsummer attire.
But the
right?
main thing I think you would pick up on right away, there's no air. You would suffocate in a second.
Well, there's air, but there's no oxygen in the air.
Well, so you just have to make all that stuff
Well,
once
so
you get
there
there.
is-
Thank you, Chuck.
And you're 1.5 times the distance that we are from the sun. So your solar energy, if you wanted to run solar panels, what's 15 squared? So it's a 1.25.
2.25 times more.
Less.
Less.
Less
So now-
sunlight.
No, you need
Okay.
2.25 times more solar panels
Yeah,
to equal
2.25, yeah.
Okay, so he's trying to change humanity by reinventing space exploration. I get that. But he's also worried about problems on Earth.
From a terrestrial standpoint, the biggest problem we need to solve on Earth this century is sustainable production and consumption of energy. This really is quite a serious problem. People really should take this quite seriously. even if you put the environmental consequences of dramatically changing the chemical composition of the oceans and atmosphere aside, we will eventually run out. If we don't find a solution to burning oil for transport, and we then run out of oil, the economy will collapse and civilization will come to an end, or as we know it.
With or without global warming.
Yeah, with or without, exactly. I mean, and so if we know that we have to ultimately get off oil no matter what, we know that that is an inescapable outcome. It's simply a question of when, not if. Then why would you run this crazy experiment of changing the chemical composition of the atmosphere and oceans by adding enormous amounts of CO2 that have been buried since the Precambrian era? That's crazy. That is the dumbest experiment in history by far.
So therefore, we need another solution here. But of course, electric cars still uses coal.
That's why you need sustainable power production, like solar and wind.
Which can still charge your car.
Yes.
There is, it's been estimated that we could save about 30% of the energy we use through conservation. We can have electric cars. We can improve transportation systems, to be sure. But the big thing, you guys, as we say about climate change, if you are opposed to government regulation now, you don't like governments now, just wait till stuff gets bad. Just wait till Floridians have to abandon their homes and Miami's half underwater, and then there's going to be regulation.
Really,
and I'll give you an example of this. World War II. Regulation happened like crazy, and everybody was very proud of it. Want to create the next great generation.
So what I neglected to mention here, and I think you should have mentioned too, was if you can start out with a $100,000 car because it's a test of concept, people like it, wealthy can buy it. But the real test is, can you make an electric car that's competitive in price to...
Absolutely.
And I'm told there's a Tesla Model 3 expected to come out, and that's priced at $35,000?
Yeah, okay. So I drove a Nissan Leaf for 3 years.
Yeah, okay.
It was about that same price.
About that same price. Elon cured me of my urges to find a flying car.
Oh.
Well, just wait till everybody's in traffic flying cars.
No. He told me what the deal is with flying cars.
Wing loading?
Let's find out.
Let me ask you, so are you sure you want a flying car?
No, but it looks cool.
It does look cool. I mean, whenever you see sort of cities and like some futuristic concept, they always throw the flying car in there. And
you can't tell me you never thought of it.
No, I've thought a lot about it.
Yeah, okay.
And there's some people I know that are working on flying cars or flying personal transport devices, if you will.
Hoverboards.
There are people working on hoverboards. I'm debating, like, should there be flying cars or shouldn't there be flying cars? I'm of two minds on that, because if there are flying cars, then, well, obviously you have added this additional dimension where now a car could potentially fall on your head and will be susceptible to weather. And of course you'd have to have a flying car where it would be like an autopilot, because otherwise forget it.
You don't want people navigating.
Yeah, it's got to be. It's got to be autopilot. But even in an autopilot scenario, and even if you've got redundant motors and blades, you're still gone from near zero chance of something falling on your head to something greater than that. And there's also a noise challenge. So
we don't know how to fly quietly.
Right.
Yeah. Okay, so I'll wait it out some longer.
Something that I do think would definitely help a lot in cities is more tunnels. Essentially with a flying car, you're talking about going 3D. And there's a fundamental flaw with cities where you've got dense office buildings and apartment buildings and duplexes, and they're operating on 3 dimensions, but then you go to the street and suddenly you're 2-dimensional.
Because it's a surface.
Yeah.
This is how New York City solved this with the subway, going underneath multiple layers of subway.
Right.
So we are actually traveling in 3 dimensions, but below the ground rather than in the air.
But I think if you were to extrapolate that to cars and have more car tunnels, then you would alleviate congestion completely.
And you wouldn't need the flying car.
You would not need a flying car in that case. And it would always work even if the weather's bad. And
it would never ice up.
It would never ice up, and it would not fall on your head.
If you've been scoring along with us, you may remember in our first segment, we listed the things he wanted to introduce to change humanity.
Right.
There's one thing he does not want to touch. Let's check it out.
I mean, I'm quite worried about artificial superintelligence these days. I think, and I've said this publicly, I think it's maybe something more dangerous than nuclear weapons. So we should be really careful about that. If there was a very deep digital superintelligence that was created that could go into rapid recursive self-improvement in a non-logarithmic way, then, that was...
And it's self-learning.
Yes. So it just could reprogram itself to be smarter and iterate very quickly and do that 24 hours a day on millions of computers. well,
Then that's all she wrote.
I mean, or something strange is going to happen.
They'll keep the docile humans and get rid of the violent ones, and then breed the docile humans.
Yeah, I mean, the utility function of the digital superintelligence is of stupendous importance.
Yeah.
What does it try to optimize? And we need to be really careful with saying, oh, well, how about human happiness? Because it may conclude that all unhappy humans should be terminated. And, that we should all just be captured and with dopamine and serotonin directly injected into our brains to maximize happiness, because it's concluded that dopamine and serotonin are what cause happiness.
Therefore
Maximize that. I'm just saying we should exercise caution.
So just to be clear, he's not talking about artificial intelligence.
Right.
He's talking about artificial superintelligence, the kind that can self-learn.
Okay, so 20% of the world's population of people does not have electricity.
Mm-hmm.
They've never made a phone call, not a cell phone call. They've never made a phone call.
Mm-hmm.
So when the superintelligence takes over Chicago or whatever, what are people in East Africa going to give a rip about? I think people have to keep in mind, computers are so reliable and they're so much part of our everyday life now. We take them for granted, but somebody is, literally or in a sense, shoveling the coal.
Okay.
What happens if you unplug the supercomputer intelligence thing?
I'm with you here.
It seems like a solvable problem.
So I'm looking at here. We have three levels of intelligence. Artificial narrow intelligence. So that's computer doing one thing better than anything, is not getting anybody's way.
A calculator.
Let it do it.
One wins at Jeopardy.
And no, that'd be artificial general intelligence, which would be general intelligence, but it's not. It's not hell bent on taking over the world.
It's that IBM computer, right?
Yeah.
Yeah, it goes across. Yeah. Which one was that? Watson.
It's Watson. Okay.
Watson. So it's the superintelligence that scares him. And I kind of agree with you, Bill. You could at some point you just unplug the dude.
Yeah.
And
well, I just think about the Colossus project, Forbin, the Colossus project. And so this is where the two superpowers on Earth have nuclear arsenals. They're controlled by computers, so they connect the two computers. And, trouble ensues. You try to unplug it, but they have their own nuclear reactors that run them.
This is the movie War Games, like all over again.
Yeah. Well, it was before War Games. It was a novel. And then a movie. But the deal is that running a nuclear power plant is not straightforward. It takes somebody shoveling the coal, a rate. Ponds,
So there's also much ado about the singularity. Ray Kurzweil. I got to get him on StarTalk because I'm just not with him on this. But this notion that somehow the world is fundamentally different before and after this singularity.
But from a historical standpoint, I could buy it.
No, we'll be different, but we're not going to be. It's not. We're going to be screaming out of the apartment. No, when machines took over our physical labor, did we say, "Oh my gosh, this is the crazy day"? No, it happened slowly, and we're fine.
Right.
Now we got people repairing machines. I don't have, so.
And there's still artisans carving the thing.
We got to get them on the show, but we can't leave people freaked out over the fate of the machines that we create and their capacity to turn us into domesticated pets. Let's find out if Elon has any positive thoughts about the future at all.
I'm quite optimistic about the future. I mean, I don't think we're about to enter a dark age. It could happen, but it's not, I think, not likely anytime soon.
Not before you get to Mars.
Hopefully not before we get to Mars. But bear in mind that...
And part of the act of trying to get to Mars is a force to keep us out of the dark ages.
I mean, there's always a chance that something calamitous could happen to Earth, either a natural or man-made catastrophe. Certainly we see that in the fossil record. And we've invented all sorts of ways of doing ourselves in that the dinosaurs didn't have. And we haven't managed to solve the asteroid problem. So, therefore, our risk is higher, okay? I'm sure people realize this. If you haven't solved the problems that have caused the prior extinctions and you've added new ones, you've not improved the situation. And that's sort of where we are right now. And there are people, there are some really smart people that are a lot more pessimistic than I am, like, the Stephen Hawkings of the world and Martin Rees, the Royal Astronomer. They're all quite pessimistic. I'm a naturally optimistic person, but I do think that there's value in establishing life insurance, which, if life as we know it is on more than one planet, then the light of consciousness as we know it is likely preserved into the future for much longer.
Here's what I'm saying. You want to become a multi-planet species, whatever effort that takes, I've said this before, it seems that it would be less effort to deflect the asteroid than to terraform Mars and ship 1 billion people there.
Yeah.
I'm with you on that.
Deflect the damn asteroid and get on with life. If you have the power to terraform Mars, you have the power to fix Earth.
Yeah, and Martian atmosphere is getting scraped off all the time.
That's what I'm saying.
Everybody,
what fears you the most? What fears you the most? We got to wrap it up. What fears you the most?
Climate change, then asteroids.
You know what I fear the most?
What?
That we lack the wisdom to understand our own fate, so that we then become victims of it, rather than conquerors.
This sounds like those who do not know the past are condemned to repeat it.
It's a version of that. Elon announces he's going to send an uncrewed mission to Mars. He and I got into a little dust up, and I was surprised to see some headlines because it largely misrepresented what I actually said publicly. Didn't so much misrepresent it, but it made more of it than I did. Maybe because they felt it could serve as good clickbait. Let's go back a few years when Elon and SpaceX was commissioned by NASA to bring cargo to the space station. Something NASA's been doing for decades. So now private enterprise is going to do it. How that fact could turn into, oh my gosh, private enterprise is going to lead the way, I didn't see how one connects to the other. Here's my point. The history of really expensive things ever happening in civilization has, in essentially every case, been led geopolitically by nations. Nations lead expensive projects. And when the cost of these projects are understood, the risks are quantified, and the timeframes are established, then private enterprise comes in later to see if they can make a buck off of it. That's perfectly normal and natural arc in the history of major funded projects. If the project does not require much money, then private enterprise could do it because it's a relatively low risk fitted into their R&D budget. Fine. I'm talking about major allocations of the resources of a civilization, like China building the Great Wall, like Europe building cathedrals and churches, a huge investment of time, energy, and effort, like the Apollo program, the Manhattan Project. All of these are instigated by either governments and, in the case of the cathedrals, praise of deity. The pyramids, add those, praise of royalty. These are forces that dislodge money from the coffers of a civilization. So what has private enterprise been doing? They've been going back into orbit, where NASA has been since 1962 with the launch of John Glenn. And so when does private enterprise lead us into space? I personally don't see that happening, because if you want to lead into space, what are you doing? You're going where no one has gone before. Often it involves risk that a company that has investors will not take, unless there's very clear return on investment, ROI. Governments don't need a financial return on investment if they can get a geopolitical return on the investment. This is how power is established, has ever been established in the world. For example, private enterprise has been doing things that NASA's been doing for the past 6 decades. By the way, they've been doing it for cheaper. I can say without hesitation, SpaceX has been advancing the engineering frontier of space exploration, especially with the spectacle of the returning of the first stage back to Earth so that you can reuse it. I've said this before. If you flew a Airbus A380 or a Boeing 747 to Europe from the United States, and when you landed, they shoved it off a cliff and rolled out another one, your trip to Europe would be really expensive. So reusability matters. So these are tremendous triumphs of SpaceX in this space, pun intended. Can I think of it as a space frontier being pushed? I can't really do that. I can't think of it that way. I said that. I said that private enterprise will do what nations have done, and they'll do it more cheaply. If there's an occasion for private enterprise to do something that nations have never done before, that's a very serious conversation in the funding room. venture capitalist. Elon, what do you want to do? Oh, I want to send astronauts to Mars. How much will it cost? A lot, possibly $1 trillion. Is it dangerous? Yes. Will people die? Probably. What's the return on that investment? I can't think of one right now. That's a 5-minute meeting. So how would Elon get to send his rockets to Mars? From the playbook of the history of geopolitics. What'll happen? The United States decides we need to send astronauts to Mars one day, geopolitically, by whatever force is operating on us. And then NASA looks around and says, you know, we don't have a rocket to do that. And then Elon says, I have a rocket, and rolls out his rocket to Mars. Then we ride a SpaceX rocket to Mars. That could easily happen. But I just want to make it clear, it's not a mission initiated by a private company. Because the money for that is not going to come from his earnings on anything else he does in space. It's going to come from taxpayers funding NASA's goals, inspired by the geopolitics of the world at that time. So I'm delighted to see that Elon and SpaceX has announced that in the coming years, they're going to send uncrewed rockets to Mars. These are vessels that are equipped to carry people, but you wouldn't send people first if you're still sort of getting the bugs out of the system. So that's great. That would be advancing a space frontier. You know why? No one has ever sent a rocket to Mars that could have carried people. That would be advancing a space frontier. I look forward to that. And I don't know enough details. Is he going to bring them back? You kind of need to do that if you're going to have people there, unless they signed up for a one-way trip. And Mars is not quite ready to receive people on a one-way trip. All right, you got to wait for the terraforming for that to happen. You'd want to bring them back. By the way, that round trip would take several years, and a minimum energy transfer from Earth's orbit to Mars orbit takes just under a year to do that. Then if you want a minimum energy return, you got to wait until Earth and Mars are properly configured once again in our respective orbits. And then you can take advantage of that configuration and then come back. So a full round trip is several years. So I look forward to this and see how that unfolds. Those are definitely the first steps. By the way, the current American program to return to the moon, it's called Artemis, has 3 planned missions. The first was an uncrewed mission to the moon. It went to the moon and came back, splashed down in the ocean. Good. Second is a crewed mission to the moon, but not land yet. Third would be a crewed mission to the moon where you land, right? Incremental steps, just as Apollo had unfolded. That's one of the reasons why there were many Apollo missions. Each one was incrementally more ambitious than the previous one. So this is how space works. If you want to stay safe in the process, especially when it involves people, crew, astronauts, and look forward to seeing what comes of that. Good luck, SpaceX. Godspeed to you.